A generation ship may be the only honest way we ever reach another star. Not a vehicle, a sealed world. People are born on it, live their whole lives on it, and die on it. Only their descendants ever arrive. Everything it launches with is everything it will ever have. We've tested that idea once. In 1991, 8 people sealed themselves inside a glass dome in Arizona. 16 months later, the oxygen had fallen to what you'd breathe at 15,000 feet, and outside air had to be pumped in. 16 months, 8 people, a door they could open. Now take away the door, and the planet. Could one sealed ship really keep 1,000 people breathing, fed, healthy, and holding together, century after century, with nothing coming in, no rescue, and no way to turn back? Tonight, you'll know what keeps a ship like that alive, what's quietly killing it the entire way, and how long it actually lasts out there. Now get yourself comfortable, hit subscribe, we begin. Before 1992, the number of confirmed planets orbiting other stars was 0. Not small, 0. Every world in our entire catalogue circled our own sun, and everything past that was inference and hope. Then, in September of 2025, NASA's tally of confirmed exoplanets crossed 6,000, and the count has kept climbing since, with more than 8,000 additional candidates still waiting in line for verification. Work out the pace, and it comes to roughly 1 new world confirmed every 2 days, on average, for more than 3 decades without pause. Rocky ones, ocean candidates, worlds sitting at exactly the right distance from their star for liquid water to survive on the surface. And somewhere in the middle of all that discovery, the question quietly changed. We stopped asking whether anywhere else out there might be livable. We started asking something harder and far more uncomfortable. Can we actually get there? Let's start with what we have actually done, because the honest answer is smaller than most people assume. On the 6th of April, 2026, 4 astronauts aboard NASA's Artemis II mission swung around the far side of the moon in a spacecraft named Integrity and set a record that had stood untouched for 56 years. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen of the Canadian Space Agency reached a maximum distance of about 406,000 kilometers from Earth, roughly 252,000 miles. They edged past the mark the Apollo 13 crew had held since 1970, and they did it with the moon filling their windows so completely that NASA's own visualization team described the view as roughly a basketball held at arm's length. That distance is the record, not a milestone on the way to something. The record, the absolute outer boundary of everywhere a human being has ever physically been. We have thrown objects toward the stars. We have never sent a person past the moon. Now hold that boundary in your mind, because we're about to measure the first step outward against it. The nearest star to our Sun is Proxima Centauri, 4.24 light-years away. That number means almost nothing on its own, so let's convert it. 25 trillion miles, 40 trillion kilometers. Still nothing. The human brain has no shelf to put a trillion on, so shrink it. Take the entire distance those 4 astronauts crossed, the farthest any human has ever traveled from Earth, the whole reach of our species, and compress it down to a single grain of sand, 1 millimeter across, sitting on your fingertip. Keep the proportions exactly. On that scale, Proxima Centauri is not across the room, not down the street. Proxima Centauri is 99 kilometers away, 61 miles, a grain of sand on your finger, and the nearest star is an hour's drive down the motorway. That is the real ratio. The nearest star sits almost 100 million times farther out than the farthest human has ever been. Which brings us to the obvious objection. We have engines now. Surely something we've built moves fast enough to close that. Something does. Voyager 1, launched in September of 1977, It stole momentum from Jupiter and Saturn in a pair of gravitational slingshots and has been coasting outward ever since. Today, it moves at roughly 38,000 miles per hour, about 61,000 kilometers per hour relative to the Sun. That's fast enough to cross the distance from Earth to the Moon in about 6 hours, a journey that took the Apollo crews 3 days. Nothing humanity has built since has left the solar system faster. Run that speed against the size of a light year, and it comes to this. Voyager 1 covers 1 light year roughly every 18,000 years. Do the arithmetic on Proxima, and you get a number that stops being a travel time and becomes something else, around 75,000 years. Let's make that real. Guess what human beings were doing 75,000 years ago? Not building, not writing. Writing was more than 70,000 years in the future. In a cave on the southern coast of South Africa, a person picked up a sharpened piece of red ochre and dragged 9 crossing lines onto a small flake of stone. Archaeologists found it at a site called Blombos. Dated to about 73,000 years old, it is the oldest known drawing made by a human hand. A ship leaving today at Voyager's speed would still be in transit to the nearest star, having travelled for longer than the entire history of human drawing. And in cosmic terms, Proxima is the easy one. Tau Ceti sits 11.9 light-years out, one of the very few Sun-like stars in our neighbourhood, and for that reason one of the most quietly tempting targets in the sky. At Voyager's velocity, the crossing runs past 210,000 years. 210,000 years ago, a human being died in a cave in what is now southern Greece. In 2019, a team led by Katerina Havati at the University of Tübingen redated the skull fragment, a specimen called Apidema 1, and published in Nature that it was at least 210,000 years old, the earliest evidence of our species anywhere outside Africa. That is the crossing time to Tau Ceti, not a voyage, a span in which an entire species can leave one continent and populate a planet. We keep reaching for dynasties as the unit here. The Ming, the Romanovs, 300 years of somebody's family holding a throne. Dynasties are the wrong unit. The right unit is evolutionary, which raises a question we have to answer before we talk about crossing anything. What, exactly, is waiting on the other side? Barnard's star sits 5.96 light-years away. It is the closest single star to our Sun, second only to the Alpha Centauri system, which is 3 stars bound together. Edward Emerson Barnard identified it in 1916. It is a red dwarf, dim and cold and utterly invisible to the naked eye, despite sitting practically next door. And for 100 years, it broke people's careers. Astronomers announced planets there. The announcements collapsed under scrutiny. Again, and again. Every claimed detection since 1916 had failed to survive follow-up. Then, on the 11th of March, 2025, a team led by Ritvik Basant at the University of Chicago published in the astrophysical journal Letters, and the century-long drought broke. 4 planets. Confirmed. They did it by measuring the star's wobble. A planet's gravity tugs its star very slightly back and forth, and if your instrument is precise enough, you can see that motion in the star's light. The team used Maroon X, a spectrograph on the Gemini North Telescope in Hawaii, combined with espresso on the Very Large Telescope in Chile. Their measurements were precise to around 30 centimeters per second. That's a star 6 light-years away, and they detected it shifting at roughly the speed of a slow walk across a room. All 4 worlds are small, between 19 and 34% of Earth's mass. Barnard E may be the lightest planet ever detected by this method at all, and all 4 are hot, whipping around their star in orbits of under 7 days. A year there lasts less than a week, but here is the sentence that matters most, and it isn't the discovery, it's what the same data ruled out. Within Barnard's star's habitable zone, the band where liquid water could exist, The measurements exclude any planet heavier than 57% of Earth's mass, with 99% confidence the nearest single star to our Sun, a century of hope, 4 worlds found, and the one place we'd want to stand swept clean. So we can find them, we can't reach them at probe speed. The obvious next thought is the one you're already having. Build a faster engine. People tried. Seriously. Between 1958 and 1965, a team at General Atomics, Ted Taylor driving the engineering, Freeman Dyson driving the theory, worked on Project Orion. The concept came from Stanislaw Ulam, and it is exactly as blunt as it sounds. You throw nuclear charges out the back of your ship and let them detonate against a massive steel plate. The plate absorbs the blast. The ship lurches forward. You do it again. And again. Thousands of times. Picture riding a ship pushed by explosions the way a surfer is pushed by waves, except each wave is an atomic bomb, and you are the surfboard. It should sound insane. It wasn't. The physics worked. They flew scale models on conventional explosives in 1959. Dyson's team had a motto: Mars by 1965, Saturn by 1970. Then, in 1963, the Partial Test Ban Treaty prohibited nuclear detonations in the atmosphere and in space. Orion did not die of physics. It died of politics. Funding was deleted entirely by 1965, and Dyson later wrote a famous eulogy for it titled Death of a Project. And you'll often hear that Orion could have reached 1/10 of light speed. Let's be precise about that, because the honest number is more sobering. In Dyson's 1968 paper Interstellar Transport, his optimistic design reached about 10,000 kilometers per second, roughly 6,000 miles per second, or 3.3% of light speed. Alpha Centauri in around 130 years. His conservative design was 10 times slower still, a voyage of some 13 centuries. Dyson himself, decades later, was blunt about it. Nuclear energy, he said, uses less than 1% of the mass involved. The velocities you get are limited to far less than 1/10 of light speed. Great inside the solar system. Not very interesting outside it. The man who designed the atomic starship stopped believing in it. Then came the next attempt. From 1973 to 1978, roughly a dozen volunteers from the British Interplanetary Society, led by former Rolls-Royce engineer Alan Bond, produced Project Daedalus, still the most detailed starship design study ever completed. Their rule was strict, current or near-future technology only, and it had to arrive within a human lifetime. Their target was Barnard's star. Daedalus would have been assembled in Earth orbit at 54,000 tons, most of it fuel, burning pellets of deuterium and helium-3, ignited by electron beams at 250 detonations per second. 2 stages. The first burns for 2 years and reaches 7.1% of light speed. The second burns for another 1.8 years and pushes it to 12%. Then the engines shut down forever and the ship coasts for 46 years in silence. 50 years to another star. On paper, it worked. Now hold the arithmetic in your hand, because this is the whole problem in 3 numbers. At 1% of light speed, Proxima Centauri is about 430 years away. At 5%, roughly 85 years. At 10%, about 43 years. Every serious interstellar proposal ever published lands somewhere in that window, 50 years to a few centuries. And yes, warp drives, wormholes, they exist. But let's be honest about where. The warp drive lives inside Einstein's equations as a valid solution that requires negative energy, a form of matter with no confirmed existence anywhere in the observed universe. Wormholes are the same story, mathematically permitted, never observed, with no engineering path anyone can point to. They are real, the way a blueprint for a building on a planet nobody has found is real. They are not doors, they are drawings of doors. Here's where the story cracks open, and it's an argument scientists genuinely have not settled. In 2006, Andrew Kennedy published a paper in the Journal of the British Interplanetary Society using Barnard's star as his worked example. He called it the weight calculation. The logic is uncomfortable. If technology keeps improving, a ship you launch today will be overtaken by a faster ship launched a century from now. Your descendants arrive to find a colony already there, founded by people who left long after you did. Your entire voyage, pointless. Mark Millis calls this the incessant obsolescence postulate. David Brin called it Zeno's paradox in reverse. The counter-argument is just as sharp. If every generation reasons that way, then every generation waits, and nobody ever leaves. The trap eats itself. Kennedy's own mathematics found a genuine minimum. Assuming exponential growth in travel speed, there exists an optimal moment. Leave then, and you beat departures made at any other time, earlier or later. But that answer depends entirely on the growth rate you assume. And if the growth rate changes, leaving earlier may be the better move after all, which means we do not know whether the correct thing to do is go or wait. We only know that both answers have teeth. One possibility remained. Stop carrying the fuel. In April of 2016, standing atop One World Observatory with Stephen Hawking beside him, Yuri Milner announced Breakthrough Starshot, a $100 million program to push gram-scale probes to 20% of light speed using a ground-based laser array. Alpha Centauri in 20 years, not 75,000, 20. In January of 2025, a Caltech team led by Harry Atwater published in Nature Photonics the first direct experimental measurement of radiation pressure on a light sail membrane. A square of silicon nitride 50 nanometers thick, 40 microns across, tethered at the corners like a microscopic trampoline, and hit with laser light while they watched it move. Real hardware, real physics, measured, not modeled. But in September of 2025, Scientific American reported that Starshot appears to be on indefinite hold. No announcement, no fanfare. Of the promised $100 million, roughly $4.5 million was ever actually spent across about 30 contracts. Its director described the program as on pause and transitioning portions to others. And even if every dollar had arrived, Starshot was never about us. A Starshot craft weighs about as much as a paperclip. Scale it up to carry a single human being, and the laser power required exceeds anything our civilization produces. Light sails carry probes. They will never carry people. So here is the conclusion the physics forces on us, and it is not the one anyone wanted. This is not an engine problem. If the crossing takes centuries, and no propulsion system on any honest drawing board shortens it below that, then the answer was never going to be a better rocket. The answer has to be a different kind of object entirely, one where the length of the voyage stops being a problem to solve and becomes a condition to live inside. Two men understood this before anyone had reached orbit. In January of 1918, Robert Goddard, the father of liquid fuel rocketry, a man who had not yet flown anything, wrote a set of private notes on interstellar migration and locked them in a friend's safe. He imagined hollowed asteroids carrying humanity outward across thousands of years. He wrote that the natures of the passengers might change across the succeeding generations. He sealed the manuscript in an inner envelope, on which he suggested the writing inside should be read only by an optimist. 10 years later, in 1928, Konstantin Tsiolkovsky published The Future of Earth and Mankind, describing a vessel he called a Noah's Ark, a colony with engines travelling for millennia. In his account, the crew changed so completely across the generations that they no longer recognized Earth as home. Both men, working independently, arrived at the same reframing. The ship is not a vehicle. The ship is a home. So let's be precise about what we are actually building, because every question that follows depends on this one definition. A generation ship is a sealed world with an engine. The people who board it will die aboard it. Their children will be born aboard it and die aboard it. Somewhere around the 5th or 6th generation, someone will finally arrive. A person who never met anyone who chose this, never saw the sky it launched under, and never signed anything. And it carries one rule that governs everything else. There is no port, no refueling stop, no resupply, no rescue. Everything it leaves with is everything it will ever have. The reactors it launches with are the reactors it dies with. The seeds, the medicine, the tools, the knowledge, the people, every atom, every skill, every idea, loaded once and never again. Accepting that means accepting something about ourselves that we have quietly refused to accept for 70 years. We are not a fast species. We were never going to sprint between the stars. We are a slow species, and the stars are reachable only at the speed of biology, culture, and patience, which raises the question that turns this from a thought experiment into an engineering nightmare. A sealed world needs power, not for a mission, not for a decade, for centuries, continuously without interruption, with no one to call and no way to stop and fix it properly. Every reactor we have ever built has a shutdown date. This one cannot. Here on Earth, power is a utility. Something arrives through a wire, and if it stops, you are inconvenienced, and then it comes back. On the ship, power is an organ. Everything runs through it. Thrust runs through it. So does light. So does heat. Because outside the hull, the temperature of interstellar space is a few degrees above absolute zero. And a hull that stops being warm does not merely get cold, it becomes a place where water freezes inside the pipes that keep people alive. Air runs through it. Water runs through it. Medicine, manufacturing, computing, the machines that grow the food and the machines that clean the air the food breathes. All of it, one chain, one source. And no gas station exists between here and there. Whatever power plant the ship launches with is the power plant it will still be running when its designers have been dead for 2 centuries. So the obvious question, how good are we at this actually? Surprisingly good. Better than most people realize. The United States Navy builds the most demanding reactors on Earth. Machines that must run continuously, silently, under a hull, in salt water, with no possibility of calling for help. The Virginia-class attack submarine carries a reactor plant designed to last the entire planned 33-year life of the ship without refueling. Not one refueling. 0. The submarine is built without a refueling hatch at all, because the engineers decided the core would outlive the vessel. Sit with that for a moment. A machine welded shut inside a metal tube, expected to deliver power without a single interruption for longer than most people stay in one career. Ford-class aircraft carriers go further. A 50-year service life, with a single midlife refueling around year 25. That is the state of the human art. Genuinely extraordinary engineering. Now multiply it. A 250-year voyage needs roughly 8 Virginia-class core lifetimes laid end to end, and there is no shipyard at year 33, no dry dock, no naval reactors program with 100,000 engineers behind it, just the ship and whoever is aboard, which means the requirements list is brutal and short. Redundant reactors so anyone can fail, independent backups that share no common failure, shielding heavy enough to keep the crew alive and light enough to accelerate, and the hardest item of all, a maintenance culture that outlives everyone who wrote it down. But you are already thinking, fusion. Surely fusion. The appeal is real. Fusion offers far more energy per kilogram than fission, and on a ship where every kilogram must be accelerated, energy density is not a preference, it is the whole argument. The trouble is a sentence nobody in the field enjoys saying. No fusion machine has yet delivered sustained net power output. Not for a year, not for a week. Experiments have crossed important thresholds, and the work is serious. But a reactor that reliably produces more usable power than it consumes, continuously for decades, does not exist yet. You cannot launch on a promise, which is exactly why in 1960, one man tried to escape the problem entirely. Robert Bussard was an American physicist working at Los Alamos. The story he told was that he was at breakfast one morning, holding a tortilla rolled around scrambled egg, and that cylinder, open at both ends, gave him the idea. He sat down and wrote a paper called Galactic Matter and Interstellar Flight, published in Astronautica Acta. His insight cut straight through the rocket equation. Every ship we design must carry its own fuel, and carrying fuel means accelerating fuel, which means carrying more fuel to accelerate that fuel. The mass ratio eats you alive. So Bussard asked, what if the ship didn't carry any? Interstellar space is not empty. It holds hydrogen, thin but real. About 1 atom per cubic centimetre. Picture a sugar cube. The air filling that same volume right now contains something on the order of 27 billion molecules, packed so densely you can feel them push back when you wave your hand. The same volume of interstellar space contains 1 atom. 1. But now, let the ship move. At a tenth of light speed, it sweeps through a colossal volume of that nothing every second. And if you could funnel it, compress it, and fuse it, you would have an engine that never runs out. Fuel tanks eliminated. Mass ratio solved. An engine that could, in principle, burn forever. It is the most beautiful idea anyone has ever had about interstellar travel. And, in 1963, Carl Sagan did the arithmetic on what it would mean. Sagan presented the work to the American Rocket Society in November of 1962, then published it in Planetary and Space Science. His conclusion is one of the most quietly staggering sentences in the literature. If a ship accelerates at 1 gravity, the exact pull you feel standing on the floor right now, nothing exotic, nothing crushing, to the midpoint of its journey, and then decelerates at 1 gravity the rest of the way, then every point in the Milky Way becomes reachable within the lifetime of the crew. Not because the ship goes faster than light, it doesn't. But as it approaches light speed, time aboard slows relative to the galaxy outside. The crew ages a few decades. The galaxy ages tens of thousands of years. They arrive, alive, at the far side of everything. Sagan's verdict was explicit. With nuclear staging, fusion reactors, and the Bussard interstellar ramjet, no fundamental energetic problem stands in the way of relativistic interstellar spaceflight. The energy was never the obstacle. That is worth holding on to, because everything that follows attacks something else entirely. Bussard had proposed the scoop. He had not designed it. In 1969, an MIT researcher named John Ford Fishback published relativistic interstellar spaceflight in Astronautica Acta and supplied the first serious answer, a specific magnetic field configuration that could reach out ahead of the ship, catch charged particles and funnel them inward. No physical scoop, no 1,000-kilometer metal umbrella, just a shaped field, invisible, doing the work. Then, apart from 2 follow-up papers in the early 1970s, the idea sat almost untouched for half a century. In 2022, 2 physicists finally went back and checked the numbers. Peter Schatzschneider works at TU Wien in Vienna. Albert Jackson is a physicist at Triton Systems in Texas, and he had known Bussard personally. They had an unusual tool, software built at the University of Vienna for calculating electromagnetic fields in electron microscopes, precise enough to model exactly the kind of field Fishback had described. They published the Fishback Ramjet Revisited in Acta Astronautica. The first half of their result is good news, and it matters. Fishback was right. The magnetic trapping works. Particles genuinely can be caught in that field and guided into a reaction chamber, and a steady 1 gravity acceleration genuinely can be sustained until the ship reaches relativistic speed. Schachtschneider's own view is that the idea remains worth investigating. Then they sized the hardware. To produce 10 million newtons of thrust, about twice the main propulsion of a space shuttle, a modest target by Starship standards, the magnetic field would need to be 4,000 kilometers across. That is 2,500 miles, a funnel wider than the continental United States, made of nothing but field lines. And that is the small number. The field would also have to be 150 million kilometers long, 93 million miles. That is one astronomical unit, the distance from the Earth to the Sun. To catch enough hydrogen, the ship would need to trail a magnetic structure stretching from where you are standing all the way to the star that lights your sky. The solenoids generating it would run to kiloton-scale mass. Their conclusion was flat. Crossing the galaxy in a Bussard ramjet within a lifetime is unrealizable. So who is right? Sagan or Schachtschneider? Here is the uncomfortable answer. Both, on different questions. Sagan's claim was about energy, and it still stands. The fuel is out there, the physics permits it, no law of nature forbids the trip. Schachtschneider and Jackson's claim is about hardware, and it also stands. Nothing we know how to build or plausibly will can make a magnet an astronomical unit long. The dream did not die of physics, it died of engineering, which is a different death, and possibly a temporary one, and nobody currently knows. A middle path exists. In 1974, Alan Bond, the same engineer who would go on to lead Project Daedalus, published a concept called the Ram-augmented interstellar rocket. The logic is elegant. Carry your fusion fuel, because you need it to be the right fuel, but scoop your reaction mass from the medium, because reaction mass is just something to throw. Limited fuel supply, unlimited propellant. It reduces the problem. It does not remove the scoop, which leaves antimatter, the densest energy store known to physics, where matter and its mirror image annihilate and convert their entire mass into energy. The trouble is that antimatter does not occur naturally in any accessible form. Every atom of it has to be manufactured. CERN's antimatter factory delivers roughly 400 million antiprotons per hour. Its alpha experiment builds antihydrogen at up to 3,000 atoms an hour and can hold them for up to 100 hours. Impressive work. Now here are CERN's own figures for what it adds up to. Run the entire facility non-stop for a full year, trap every atom and annihilate the lot at once, and you would release a few thousandths of a joule, which CERN compares to the energy of gently tapping a phone screen with your finger. Take every antiproton the factory makes in that year instead, and you get about 500 joules, enough to light a 100-watt bulb for 5 seconds, and you'd have spent a nation's worth of electricity to get it. The production process returns roughly 1/10 billionth of the energy you feed into it. Then comes the wall. Antimatter cannot touch anything. Contact with ordinary matter, a wall, a speck of dust, a molecule of leaked air, means immediate annihilation. It must be suspended in vacuum by magnetic fields that never fail, powered by the reactor it is supposedly there to replace. So the near-term verdict is unglamorous and completely solid. Fission keeps the lights on. Everything else depends on it. That's the power. Now the harder half. Because a reactor only buys you the chance to attempt something we have never once achieved, keeping people breathing without any input from outside. The International Space Station does this today, and does it well. Its oxygen generation system runs electrolysis, an electric current splitting water into hydrogen and oxygen. The oxygen goes to the cabin. The carbon dioxide removal assembly pulls the crew's exhaled carbon dioxide through beds of zeolite, a porous crystalline mineral that traps the molecules, then bakes the beds and vents them to space. A Sabatier reactor takes the leftover hydrogen and the captured carbon dioxide and makes water and methane. The methane goes overboard, the water goes back into the loop. It is genuinely brilliant chemistry, and it is sized for 7 people. A ship needs thousands, supplied biologically, continuously, forever, with nothing coming in. We have tried that exactly once, at scale. On the 26th of September, 1991, 8 people sealed themselves inside a 3-acre glass world in the desert near Oracle, Arizona. Biosphere 2 held a rainforest, a savanna, a desert, a mangrove wetland, an ocean with a coral reef, and a farm. Underneath it ran a welded stainless steel liner. Above it, 6,500 windows. They intended to stay 2 years. Almost immediately, the oxygen began to fall. Slowly, quietly. Across 16 months, it dropped from 20.9%, ordinary sea level air, to 14.2%. By the crew's own account, that is the equivalent of living at 15,000 feet, about 4,600 meters, permanently, without ever acclimatizing. Half of them developed symptoms of altitude sickness, sleep apnea, chronic exhaustion. Simple tasks became work, and nobody could find where the oxygen had gone. Here is the contradiction they were staring at. If oxygen is disappearing, something must be consuming it, and consuming oxygen produces carbon dioxide. So carbon dioxide should have been climbing to match, molecule for molecule. It wasn't. The books did not balance. Oxygen was vanishing, and its accounting partner never showed up. Then the crew's physician, Roy Wolford, sat down one day and found that he could not add a column of numbers. That was the moment everyone agreed they had reached a breaking point. Oxygen was injected from outside. The closure claim broke on its own terms. The answer came in 1994 in a paper in EOS by Jeffrey Severinghaus, Wallace Brucker and colleagues, and it is one of the most quietly frightening results in the history of life support. Half the puzzle was the soil. The designers had loaded it with organic matter to grow good crops. The crops thrived. So did soil microbes, which respired that organic matter, consuming oxygen and producing carbon dioxide far faster than the plants could photosynthesize it back. The other half was the building. The concrete was eating the air. Exposed, still curing concrete absorbs carbon dioxide and locks it away as calcium carbonate. Inside Biosphere 2, that carbonation ran roughly 10 times faster than in ordinary outdoor concrete. Severinghaus and his colleagues calculated that the structure had swallowed somewhere around 750 kilomoles of carbon dioxide since closure, about 33 tons, 36 US tons, the weight of a fully loaded truck, absorbed into the walls where nobody thought to look. The oxygen had not vanished. It had been moved, by way of the air, into the building itself. Think about what that means. The failure was not a broken machine. Every machine worked. The failure was that a structural material, chosen for strength, priced by the cubic yard, drawn by an architect, silently joined the life support chemistry uninvited. Nobody had modelled the walls as a living organ, because walls are not alive. On a generation ship, everything is in the loop whether you invited it or not, which is why the serious programs stopped trying to build worlds. Russia's BIOS 3 at the Institute of Biophysics in Krasnoyarsk went the opposite direction. 315 cubic meters, about 11,000 cubic feet, roughly a large house, of underground steel, finished in 1972, divided into 4 compartments for up to 3 people. Its longest run held a 3-person crew for 180 days. Air and water loops closed to nearly 100%. Food to about 80%. They imported dried meat. They dried the human waste and stored it rather than recycling it. Honest, partial, measured. The European Space Agency's Melissa takes the same philosophy further. 5 compartments: microbial bioreactors, wet oxidation, filtration, and a higher plant chamber growing crops alongside cyanobacteria, modelled on a lake ecosystem with a pilot plant in Barcelona. The difference from Biosphere 2 is the whole point. A biome is one system, and when it goes wrong everywhere at once. A compartment can be isolated, measured, and fixed. And it gives us the word that governs everything: closure. The fraction of the crew's needs the ship recycles rather than resupplies. Water is where closure gets tested hardest, because water failure has the shortest fuse of anything aboard. Air runs out over hours. Food runs out over months. Water runs from crisis to fatal in days. The ISS is world-class at this. A brine processor assembly, installed in 2021, extracts the last usable water out of urine brine using warm, dry air and specialized membranes. Before it, total recovery ran 93 to 94%. With it, NASA demonstrated 98%, and NASA has set roughly 98% as the minimum threshold for any crewed Mars mission. 98 sounds like a pass. On a 2-year mission it is. On a 200-year one, that 2% is a bill that arrives every single cycle, forever, and the ship has nowhere to send it. Membranes degrade. Water locks itself into organic waste that never fully composts. Every loop leaks. Food follows the same logic. High-yield staples under hydroponics with LED spectra tuned to what the plants actually use, but also real soil, because soil carries the microbial resilience that clean water never will. Animals have to earn their mass in fats, in micronutrients, and in redundancy when a harvest fails, which is why the serious proposals reach for insects, rabbits, chickens, and tilapia rather than cattle. They turn waste into protein far more efficiently, in far less space. And medicine is worse than all of it, because medicine cannot be grown. Drugs expire, instruments wear out, calibration drifts, and the specialist, the one person who knows what a failing pump sounds like before the alarm, cannot be replaced. None of this is fantasy work, and that is worth saying plainly. Every problem here, closure, recycling, reactor lifetime, bioregeneration, is the same problem NASA and ESA must solve for a lunar base and a Mars habitat. The Starship is simply the version with no mercy in it. But look back at what actually happened inside that glass building in Arizona. The oxygen sensors worked, the chemistry was sound, the mistake was invisible, silent, and hiding in the concrete. And it was found because human beings noticed, measured, argued, and eventually understood. The alarm that mattered was not an instrument. It was a physician discovering he could no longer add a column of figures. Every reactor, every membrane, every crop, every loop on the ship has one shared dependency, and it is not uranium, and it is not water. Someone has to notice, someone has to care enough to look, someone has to still understand the machine, which raises the question we have been carefully avoiding. What happens to the people? Start with what a human being is, biologically speaking, not what we think we are, what we were shaped by. We are an animal built for horizons, for weather that arrives without warning and changes the light, for seasons, cold that becomes warm that becomes cold again, on a rhythm our bodies still keep whether we ask them to or not. We were built for a sensory world that never repeats itself. Think about how many distinct things you smell today without noticing a single one of them. Think about the fact that no sky you have ever stood under has looked exactly like any other sky. Every one of those things is a signal, and the brain, it turns out, is not a passive recipient of signals. It is a thing that is maintained by them. Now build the ship. The sky is metal. It has a rivet pattern, and after a year you know it. The horizon does not recede. It curves upward and comes back around to where you're standing. Walk far enough in one direction and you will find your own footprints. Weather happens because a fan turns on. Seasons happen because a lighting engineer wrote them into a schedule 2 centuries before you were born. Nothing about that is dangerous. That's what makes it worth studying. And, remarkably, we have already run a version of the experiment. Neumayer Station 3 sits on the Ekstrom ice shelf near the Weddell Sea in Antarctica. Penguins are the nearest neighbours. In winter, the sun does not come up. Between arrivals, 9 people lived there for 14 months, 5 men and 4 women, and for 9 of those months they were completely cut off from the outside world. Alexander Stahn, working with the Charité University Hospital in Berlin and the Max Planck Institute for Human Development, decided to find out what that does to a brain. His team scanned the expeditioners before they left, and scanned them again when they came back. They matched them against 9 control subjects of the same age and sex who stayed home. They measured cognition throughout. They drew blood. The results came out in the New England Journal of Medicine in December of 2019, and they are quietly disturbing. The dentate gyrus had shrunk. Here is what that means. The dentate gyrus is a small structure buried inside the hippocampus, and it does 2 jobs that matter enormously to you personally. It is one of the very few places in an adult human brain where genuinely new neurons are born, and it is central to turning the events of a day into a memory you can find again later. It is, in a real sense, where today becomes something you can look back on. In the 8 expeditioners who could be scanned, that structure lost between about 4 and 10% of its volume across the expedition, an average of roughly 7%, compared to the people who stayed home. 14 months of monotony took a measurable bite out of the part of the brain that makes new memories and new cells, and the blood explained why. BDNF, brain-derived neurotrophic factor, is a protein that lets newborn neurons survive and wire themselves in. Without it, new cells appear and then quietly die. Think of it as fertilizer. The seeds still fall on the soil. Nothing takes root. Across the expedition, BDNF fell by an average of 45%, close to half, and the timing is the part that should make you sit forward. Levels had already dropped below baseline after only 3 months, and they had still not recovered a month and a half after everyone came home. Then the cognition tests. When you take the same test repeatedly, you normally get better at it. That learning effect was reduced in the expeditioners, and reduced in proportion to how much dentate gyrus each person had lost. The ones who lost the most did the worst on spatial awareness and on selective attention, which is the ability to ignore the things that don't matter so you can see the thing that does. Stahn's own explanation is the clearest thing anyone has said about this. The brain, he says, is a bit like a muscle. It will not adapt if you expose it to the same stimuli all the time. But he said something else too, and it matters. Given the small number of participants, Stahn cautioned, the results of our study should be viewed with caution. 9 people, 1 station. No way to control for 100 confounding variables. The altitude, the cold, the sleep disruption, the hypoxia, the fact that people who volunteer for Antarctica are not a random sample of humanity. He knew it. He said it out loud. In July of 2025, a much larger study arrived, and it complicates the picture in a way that is genuinely unresolved. Concordia Station sits at Dome C on the Antarctic Plateau, 3,200 meters up, about 10,500 feet, so the air is thin enough that the crew live in permanent mild oxygen starvation. Winter averages minus 76 degrees Fahrenheit, roughly minus 60 Celsius. The nearest coastal station is 685 miles away, about 1,100 kilometers. The landscape is flat and barren in every direction. For several weeks the sun does not rise. Nobody can reach you, and you cannot leave. A team led by David Roalf and Matthias Basner at the University of Pennsylvania, working with Ruben Gurr and a large international group, scanned 25 crew members from 2 winter-over crews, 3 times as many people as the Neumayer study. Before departure, within 16 days of leaving Antarctica, And again, about 5 months later, they found the decline. Grey matter dropped in the temporal and parietal lobes, in the hippocampus, in the pallidum, in the thalamus. White matter dropped. The brain's ventricles, the fluid spaces inside it, got bigger. And then, 5 months later, almost all of it came back. Everything except the thalamus returned to baseline. The word in their title is transient. So which study is right? Here is the honest answer, and it is not a dodge. Alexander Stahn is a co-author on both. This is not two camps fighting. This is one field arguing with itself in public, which is what good science looks like from the inside. The 2025 team points out fairly that Stahn's group scanned people several weeks after they got home, by which point some changes may already have healed. But Stahn's team used higher resolution scans that could isolate the dentate gyrus specifically, and the newer study could not. They were not quite measuring the same thing at the same resolution, and the authors themselves note that with their sample size, none of their correlations survive strict statistical correction. What they did find is useful and hopeful. Better sleep, more of it, and better quality, tracked with less brain volume loss. Time spent in the gym tracked with volume preservation. Countermeasures may exist, and one finding is just plain strange. Crew members who lost more brain volume tended to perform better on several cognitive tests. That is the opposite of what anyone expected. The authors call it puzzling, speculate that shedding neural resources under prolonged stress might somehow be adaptive, and then honestly admit they don't know. So the state of the evidence is this. Something real happens to the brain in isolation. It may substantially reverse. Sleep and exercise seem to help, and nobody yet knows what any of it means over a timescale longer than a year. But all of that misses the thing that actually matters here. Every single person in both studies knew they were going home. There was a date, there was a plane, there was a moment, however far off, when the door would open onto grass, submarine surface, Antarctic crews rotate out at the end of the austral summer, research outpost close, prisons release. Every isolation experiment humanity has ever run, every one, carries an expiry date printed somewhere in the subject's mind, and that date is doing work we have never been able to measure because we have never been able to take it away. The ship takes it away. There is no rotation, no relief crew, no date. For the people born aboard, the metal sky is not a 14-month assignment. It is the sky. We have no data on that. None. We cannot get any. And there's a second thing Earth quietly gives us that we almost never name. Distance. On Earth, the ultimate conflict resolution mechanism is not therapy or mediation or law. It is the ability to walk away, change jobs, change cities, stop answering, leave the room, and don't come back. Almost every serious human conflict in history has been survivable because, in the end, somebody could go somewhere else. Aboard the ship, the person you fought with this morning sits down across from you at dinner, and tomorrow, and in 30 years, at your daughter's wedding, because there is nowhere else for either of you to be, which leads to a claim that sounds strange the first time you hear it, and obvious the second. Governance may matter more than reactor design, and it gets a fraction of the attention, because here is the hole underneath the whole enterprise. The founders consented. They chose it. They stood on a launch pad, understood the terms, and said yes. Their children never did. Their grandchildren never did. And the person who finally opens the hatch at a new star, 5 or 6 generations down, never signed anything, never met anyone who did, and lives under rules written by ancestors who cannot be argued with, appealed to, voted out, or even properly imagined. The closest thing history offers is a single page. On the 11th of November 1620, the Mayflower sat off Cape Cod, badly off course, outside the jurisdiction of the charter that was supposed to govern the passengers, and there had been what the record politely calls mutinous speeches. So 41 adult men, out of about 102 people aboard, signed roughly 200 words agreeing to form a civil body politic and obey laws made by majority consent. 2 facts about that document are worth holding together. First, 1 page, 1 crossing, written the week they arrived. Second, John Carver, elected the colony's first governor under it, was dead by April. So were many of the men who signed. The agreement outlived its authors by months, and then it had to govern people who had not been in the room. Now stretch that to 250 years and no land. The proposal on the table is a layered constitution, an inviolable core that cannot be changed, plus revisable law on top of it. Bedrock and topsoil. The topsoil is theirs to rework. The bedrock keeps the ship from voting itself out of existence in a bad decade, and the trap in that design is immediate. Inviolable means the dead hold a permanent veto. Every generation aboard inherits a decision made by people they never met, which they cannot overturn in a world those people never saw. There is no clean answer. Anyone who tells you otherwise is selling something. The biology is, if anything, less settled than the politics. Genetic diversity is not a feature, it's a reserve. It's the hand of cards a population hasn't played yet. The variation that lets somebody survive a challenge nobody predicted. A pathogen, a shift in the food, a subtle change in the radiation environment. Shrink the population, and you shrink the hand. What follows is well documented on Earth, in island communities and geographically isolated populations, inbreeding depression, falling fertility, immune systems that handle novelty badly. So, the obvious question, how many people do you need? Here is where the field falls apart. Cameron Smith is an anthropologist at Portland State University. In 2014, writing in Acta Astronautica for the original Project Hyperion effort, he ran the population genetics for a roughly 5-generation voyage and came back with a founding population of 40,000 people, with an effective breeding population of at least 10,000. His optimized range ran from about 14,000 up to 44,000. His reasoning was blunt and drawn from the natural world. Genetically healthy vertebrate populations almost never sustain themselves below about 5,000 individuals. 4 years later, Frédéric Marin, an astrophysicist at the Strasbourg Observatory, and Camille Belloufi, a particle physicist, published a number that is not slightly different. It's a different universe. Their tool is a Monte Carlo code called Heritage, a simulation that doesn't do statistics on a population, it builds one. Every simulated person ages, pairs, conceives or doesn't, suffers accidents, becomes infertile, dies. Run the journey 100 times and see how many ships arrive with a healthy crew. Their answer for a 6,300-year voyage to Proxima Centauri B, 98 people. 98. Enough to fill a small restaurant. Their simulations are precise about the edges too. Start with 25 breeding pairs and forbid inbreeding entirely, and the mission goes extinct in about 50% of runs, give or take 15. Start with 32 people, and the success rate hits 0, and the field between those poles is scattered. Moore, in 2003, landed at 150 to 180. A separate code called Evolve, built to include mutation and drift, returns roughly 2,000, and about 2,000 still, even when deleterious mutations are added on top. Marin's own later work, once genetics went into Heritage, gave 100 to 500 at departure, from 98 to 44,000, a factor of more than 400. Now, before you decide someone here is being careless, they aren't. Marin and Belloufi say plainly that 98 is a lower limit under deliberately conservative assumptions, and that their code at that time did not include mutation, migration, selection, or drift at all. Smith's figure wasn't a Monte Carlo simulation. They are answering different questions with different tools, but that is precisely the finding. The most basic specification of the entire object, how many human beings to put aboard, is not converged, not close. And underneath the head count sits something colder. Hermann Müller described it. In a population where genomes don't get reshuffled, once the individuals carrying the fewest harmful mutations happen to vanish by chance, nobody can ever be born cleaner again. The floor rises, it never falls. A ratchet, a wrench that only turns one way. Every click is permanent. Michael Lynch and colleagues took it further and named the endgame mutational meltdown. Fewer healthy individuals, so a smaller population, so faster genetic drift, so more damage locked in, a loop that feeds itself downhill toward extinction. Sex is the defense. Recombination shuffles the deck, and a small population can, in principle, clean itself, but shuffle a deck of 9 cards, and you will keep dealing the same hand. And here the science pushes back on itself again. Recent modelling, a branching process analysis published in the Journal of Mathematical Biology, found that mutational meltdown does occur, but does not determine when extinction happens. The loop is real. Whether it's the thing that actually kills you is open. One elegant answer exists. Bring frozen gametes and embryos. A ship of 1,000 people could carry the genetic variety of 50,000, a library vastly larger than the reading room. Every generation could draw variation from founders who died on Earth centuries earlier. Cryopreservation is routine medicine today. Century-scale viability is not solved and cannot be, because nobody has had a century to test it. We are guessing, honestly, and calling it a guess. Which brings us to the collision this entire endeavour has never resolved. Read Moran and Belufi's own method. To make 98 people work, their simulation applies what they call adaptive social engineering principles, yearly evaluations of the vessel population, offspring restrictions, breeding constraints. Say that in plain language. Who has children, when, and with whom? Decided by the ship. That isn't villainy. It's arithmetic. Below a certain population, reproduction stops being private life and becomes infrastructure, as load-bearing as the reactor, and managed the same way. Nobody has proposed a version of that anyone would want to live under. That is the honest state of the art. Project Hyperion's 2025 design brief specified 1,000 people plus or minus 500, sitting almost exactly in the middle of a range on which the field cannot agree for a voyage lasting centuries. All of it, the shrinking hippocampus, the constitution written by the dead, the 98 versus the 40,000, rests on one assumption we haven't examined, that the people inside are only fighting each other and their own biology. Look again at Marin's most recent genetics work, published in February of 2025. Buried in it is a sentence that reframes everything. For a large crew, the genetic numbers hold steady across centuries, but the results, he writes, are completely different if the shielding built into the hull fails to protect the crew from high-energy cosmic rays and the showers of secondary particles they create. Every population model we just walked through has that clause underneath it, because deep space is not empty, and it is not neutral. 2 things keep you alive right now that you have never once thought about. The first is a magnetic field. Deep inside this planet, an ocean of molten iron churns, and that churning generates a magnetic field that reaches tens of thousands of kilometers out into space. Charged particles arriving from the galaxy hit it and slide around it, the way water in a stream parts around a boulder without ever touching it. You do not feel this. You cannot see it. It has been working every second of your life. The second is the air. We think of the atmosphere as something we breathe. It's also armor. Weigh the column of air standing directly above you, and it comes to roughly 10 tons for every square meter of ground, about 1,000 grams pressing down on every square centimeter. That's the layer a cosmic ray has to chew through before it reaches you. Hold that number, 1,000 grams per square centimeter. It will matter in a few minutes, more than you expect. The ship has neither of these, not reduced, not weakened, absent, from the day it launches until the day it arrives, in every direction, forever. So, what is actually out there? Galactic cosmic rays. And the name is misleading, because these are not rays in any sense you'd recognize. Most of them get accelerated by supernova remnants, the expanding shock fronts of stars that exploded, sometimes millions of years ago, sometimes in a completely different part of the galaxy. The shock wave keeps whipping particles faster and faster until they're moving at a substantial fraction of light speed, and then they escape and drift across the Milky Way, essentially forever. What arrives is not light, it's matter, bare atomic nuclei, mostly protons, some helium, and a small but vicious fraction of heavy nuclei like iron, traveling near the speed of light. Here's the distinction that matters. An X-ray is a photon. It passes through you, and mostly nothing happens. An iron nucleus at near light speed is a microscopic cannonball with a mass of 56 protons behind it. It doesn't damage a cell. It drills a track through a column of them, leaving a line of wreckage behind it like a bullet through a stack of paper, and they penetrate practical shielding. That's not a design flaw. That's what practical means here. Now the numbers, and each one needs its anchor. In free space, the annual dose equivalent to the blood-forming organs, the bone marrow that makes your blood, which is the tissue radiation biologists worry about first, runs to roughly 500 millisieverts a year. Mars, by comparison, is generous. The radiation assessment detector aboard NASA's Curiosity rover has been measuring the surface since 2012, and it logs about 0.64 millisieverts a day, roughly 230 millisieverts a year, less than half of free space, because Mars at least gives you a thin carbon dioxide atmosphere and a planet blocking half the sky. And Earth? The UN's Radiation Committee long put the world average from natural sources at 2.4 millisieverts a year. Their latest assessment revised that upward to about 3, not because the planet became more radioactive, but because we finally measured radon properly in enough places. So put those side by side. Free space delivers roughly 170 times Earth's natural background, every year, to every person, for every generation, from launch to arrival. Now make it personal. During the NASA twin study, Scott Kelly spent 340 days in low Earth orbit, and NASA recorded his effective dose at 146 millisieverts. In under a year, he absorbed roughly 50 years' worth of Earth background radiation, and Scott Kelly was inside a spacecraft, inside the magnetosphere, in the safest place a human being has ever been outside the atmosphere. That is the protected case. So the fix is obvious, and you're already thinking it. Add shielding. Put mass between the crew and the sky. Everyone thought that. For decades, the entire space radiation shielding community operated on one assumption that seemed too obvious to question. More shielding means less risk. Then NASA checked. A team at Langley Research Center, Ryan Norman, Martha Cloudsley, Tony Slaba and colleagues, ran the Advanced Radiation Protection Thick GCR Shielding Project, and their models produced a result that nobody wanted. The dose does not keep falling. Plot dose equivalent against aluminum thickness and the curve drops, bottoms out somewhere around 20 to 30 grams per square centimeter. That's a slab of aluminum roughly 7 to 11 centimeters thick, call it 3 to 4 inches, and then it turns around and climbs back up. Add more aluminum, get more dose. Here is why, and it is horrible in its simplicity. The shield does not absorb the cosmic ray, it shatters it. When an iron nucleus traveling near light speed slams into an aluminum atom, both come apart, and the wreckage sprays forward as a shower of secondary neutrons and light particles. Neutrons are biologically worse than what you started with. They're uncharged, they pass through matter with contemptuous ease, and they deposit their energy inside tissue. Think of it as trying to stop hail with a chain-link fence. The fence does not stop the hail. It turns big hail into a lot of small hail, and the small hail goes right through. Now, you should be skeptical of a model result this counterintuitive. So were they. They verified it with multiple independent Monte Carlo and deterministic radiation transport codes. Then they built the experiment. At the NASA Space Radiation Laboratory at Brookhaven, they fired beams of protons, helium and iron nuclei into aluminum targets 20, 40 and 60 grams per square centimetre thick, and put detectors behind them to count what came out the other side. First of their kind measurements, the minimum held, and the trend continues out past 100 grams per square centimetre, at which point they stopped calculating, because nobody would ever build a ship that heavy, which produces the sentence that reframes this entire problem. A minimum dose exists that cannot be reduced by adding shielding, so mission duration becomes the only remaining lever for keeping accumulated dose inside acceptable limits. Mission duration is the only lever, and a generation ship's mission duration is 4 centuries. But that finding comes with a genuine escape route, and it's elegant. Polyethylene shows no such minimum. The curve just keeps falling. The reason is hydrogen. A hydrogen nucleus is a single proton, almost exactly the same mass as the neutron trying to get past it. And that matters because of something you already understand from a pool table. Hit a cue ball squarely into another cue ball, and the first one stops dead. All the momentum transfers. Hit a cue ball into a bowling ball, and it bounces back, barely slowed. Aluminum is the bowling ball. Hydrogen is the cue ball. High hydrogen material soaks up neutron momentum efficiently, and because its nuclei are so light, there's almost nothing there to fragment into heavy secondaries. And here's the part that should make you sit up. The ship is already carrying an enormous quantity of hydrogen, and it isn't polyethylene. It's water. Wrap the habitat in water tanks, and every litre does 2 jobs at once: life support reserve and radiation shield. The substance the crew drinks is the substance that stops the iron nuclei. It's the most efficient idea in the entire field, because that mass was going aboard anyway. Except mass is exactly the problem. 20 grams per square centimetre is 200 kilograms for every square metre of hull. Shield a surface the size of a tennis court, and you're carrying about 50 tons. Now shield a habitat kilometres long, and remember that every one of those kilograms has to be accelerated up to cruise speed, and then decelerated again at the far end. You pay the energy bill twice, for mass whose only job is to sit still and be hit. Active magnetic shielding, giving the ship its own artificial magnetosphere, its own boulder in the stream, remains genuinely attractive and genuinely far from ready. It needs a substantial technological advance that nobody can currently schedule. That's the invisible sky, now the physical one. In 1946, an astronomer named Fred Whipple, the same man who would later figure out that comets are dirty snowballs, proposed something that sounds backwards. Don't armour the hull. Put a thin sheet of metal a short distance in front of it and leave a gap. The bumper is not supposed to stop the impactor, it's supposed to destroy it. A particle arriving at hypervelocity hits that thin sheet and both simply cease to be solid. The projectile and a piece of the bumper vaporize together into an expanding cloud that fans out across the gap. By the time it reaches the real hull, one concentrated punch has become a wide, diffuse slap. It works beautifully. The International Space Station carries over 100 different shield configurations, tuned to different risk zones, and NASA rates the design against debris up to about a centimetre across, at relative velocities reaching 18 kilometers per second, about 11 miles per second. Now scale it. At a tenth of light speed, the ship is moving at 30,000 kilometers per second, nearly 19,000 miles per second. That's about 1,700 times faster than the fastest impactor Whipple shield is designed for, and kinetic energy scales with the square of speed. The same speck of dust that the ISS is built to survive arrives at a generation ship carrying nearly 3 million times the energy. In February of 2017, Thiem Huang, Alex Lazarian, Blakesley Burkhart and Abraham Loeb published a paper in the Astrophysical Journal that finally put numbers on this. They modelled a craft crossing to Alpha Centauri at 20% of light speed. Interstellar dust erodes the surface, not gradually, violently. Each grain arrives with enough energy that the surface atoms it touches explosively evaporate, blowing a crater. Do that continuously for the whole crossing, and roughly 0.5 millimetre of surface simply leaves. Follow-up work at Lawrence Livermore found that more than 0.5 millimetre of quartz could be evaporated away, and more than 3 millimetres melted. Then the gas. Heavy nuclei, iron in particular, don't erode the surface, they tunnel into it, leaving damage tracks only nanometers wide but reaching a few millimeters deep, rewriting the material's internal structure as they go. And a curious detail, which is also a clue, graphite handles this far better than quartz. A highly conductive material dumps the energy sideways through the whole structure before a track has time to form. The material's ability to spread heat is a radiation defense. Nobody would have guessed that from first principles. Then the NASA Starlight collaboration found a mode nobody had modelled at all. John Drobny, Alexander Cohen, Davide Corelli, Philip Lubin, and colleagues showed that at relativistic speed, hydrogen and helium from the interstellar medium don't just strike the hull, they implant. They bury themselves below the surface and, being noble and stubborn, they stay there, diffusing very slowly, accumulating. Eventually they coalesce into bubbles. The bubbles push upward and blister. The blisters rupture and the surface exfoliates, peels away and flakes. The comparison the authors themselves reach for is the one that lands hardest. This is the same failure mode that eats the metal walls inside fusion reactors, where plasma-facing components are slowly turned to foam from the inside out. The hull isn't being scratched, it's being turned into a different material, and every one of those figures was calculated for a 20-year probe flight. Run it for 400 years. The bumpers erode, the hull develops microstructural fatigue, the slow, invisible crystalline damage that precedes a crack. This, incidentally, is why the chrysalis design that won Project Hyperion is a cylinder 58 kilometers long, 36 miles, and comparatively narrow. Its team said so directly. A long cylindrical geometry minimizes the frontal cross-section, which minimizes both the shielding you need and the structural stress you take. It's shaped like a needle because it has to plow through the galaxy for 4 centuries, but eventually something gets through, and when it does, the repair falls to people 12 generations removed from anyone who ever drew the thing, which brings us to the deepest problem in this entire subject, and the one almost nobody models. Every spacecraft humanity has ever flown is backed by an entire industrial civilization standing behind it. When something breaks on the ISS, a person in Houston who has spent 30 years on that exact subsystem picks up a phone. There's a factory that can make the part, there's a university that trained the engineer, there's a supply chain, a test rig, a documentation archive, and a rocket that can carry the replacement up. The ship has none of that, It has whoever happens to be aboard that day. And the archive is not the answer, for two reasons. The first is physical. Storage media rated reliable for decades are not rated for centuries, and certainly not for centuries inside a radiation environment where every stored bit is being slowly and silently rewritten by particles from dead stars. The library is decaying while nobody reads it. The second reason is deeper, and it's a distinction worth holding on to. Information is stored data. Knowledge is the understanding that improvises when the manual doesn't match the machine in front of you. Every experienced engineer knows the moment. You open the panel, and it doesn't look like the diagram, because someone modified it in year 60 and the note got lost. Information cannot help you there. Only understanding can, the kind that comes from having taken 100 of these apart, from having had a mentor stand behind you and say no, listen to it. And the ship needs that depth in reactors, in closed ecology, in chemistry, in agronomy, in medicine, materials science, navigation, computing, structural engineering. Everyone at genuine expert level, continuously, for 400 years, in a population of about 1,000 people. Anthropologists have a term for the thing standing in the way: cultural transmission fidelity. How accurately a body of understanding passes from one generation to the next. And the finding is not comforting. Accurate transfer is never automatic. Every generation is a lossy copy of the one before it. Universities, apprenticeships, guilds, peer review. Every one of those institutions evolve precisely because knowledge decays without deliberate machinery to stop it. Now add drift. Generation 1 remembers Earth, the smell of rain, an argument with a brother who stayed. Generation 5 inherits Earth as a story. The destination stops being a plan and becomes a promise made by great-grandparents on everyone's behalf to people who never got a vote. Which is why the Chrysalis team proposed something that sounds absurd until you understand what it's for. The first generations would live in isolated Antarctic conditions for 70 to 80 years before boarding, not to train a crew, to grow a culture, and then find out whether it survives its own children. Because here is what makes the knowledge problem the most dangerous of all of them. A reactor fault trips a light. A hull breach sounds a klaxon. A failing crop shows up as a number in a yield report. Every physical failure on that ship announces itself. Knowledge loss announces nothing. There is no gauge for it, no sensor, no threshold. It accumulates in complete silence across decades, invisible in every metric the ship tracks, and it surfaces on exactly one day. The day someone opens a panel, looks at what's inside, and doesn't understand what they're looking at. By then, the last person who did has been dead for 80 years. So the ship must survive a sky with no shield, a medium that erodes it, an archive that decays, and a slow forgetting nobody can measure. And it must do all of that while people live entire lives inside it. Which is why the most seductive idea in this whole field is the one that makes every single one of those problems disappear. What if nobody had to live through it at all? Sleep through it. That's the shortcut. And you have to sit with how completely it works. Because on paper it doesn't solve one problem. It deletes every problem we've built. Put the crew into torpor. Keep a small rotating watch awake. A handful of people at a time, a few years each, then back under. Nobody endures decades of a metal sky, because nobody experiences the decades. Nobody is born into a world they didn't choose, because nobody is born. The engineer who trained on Earth is the same engineer who opens the panel at the far end, so the knowledge never decays. There's no constitution written by the dead, because the founders arrive. There's no consent problem, no genetic bottleneck, no cultural drift. The people who board are the people who step off. It is the most elegant idea anyone has had about interstellar travel, and it makes almost everything we've discussed simply evaporate. And it does not exist. True suspended animation in humans is not partially achieved, not experimentally demonstrated, not nearly there. It has never been done. What we have is cold. Cooling a body slows its chemistry, and medicine uses this every day. After a cardiac arrest, doctors cool patients to somewhere around 32 to 36 degrees Celsius, roughly 90 to 97 Fahrenheit, and hold them there for about a day because a cooler brain survives injury better. Deep hypothermia, formally, means a core temperature below 28 Celsius, 82 Fahrenheit. As a rough rule, metabolic rate drops by about half for every 6 degrees Celsius you take away. Then there's the extreme end, and it's genuinely astonishing. Surgeons operating inside the aorta sometimes need to stop the blood entirely, so they chill the patient to somewhere between 14 and 20 degrees Celsius, 57 to 68 Fahrenheit, switch off circulation, and work in a bloodless, motionless body. The heart is not beating. The brain shows no activity. It is, quite literally, carefully managed clinical death. Now hold the two numbers together. At normal body temperature, stop the blood, and the brain suffers permanent damage in about 5 minutes. At 14 degrees, you get 30 to 40 minutes. 40 minutes. That is the record. That is the deepest, longest, most controlled suspension of human metabolism that medicine has ever achieved, and it is measured in tens of minutes. The voyage is 400 years. Run that ratio, and it comes out at roughly 5 million to 1. We are not close to this. We are not in the same order of magnitude as close, but serious institutions are working on it anyway, and one of their results is genuinely unexpected. The European Space Agency treats this as real research, not daydreaming. Hibernation sits inside its Sci-Spacy Science program and its Advanced Concepts team, with a dedicated topical team of outside scientists, after ESA's own Future Technology Advisory Panel flagged it as a key enabling technology for spaceflight. In 2019, the Sci-Spacy team called in ESA's Concurrent Design Facility, a room built so that specialists from every mission discipline can sit together and design a spacecraft in real time, and ask them to assess what human hibernation would actually do to a mission. The study kicked off on the 3rd of April, ran across 5 sessions, and took as its reference an existing plan to send 6 humans to Mars and back over 5 years. The picture they drew is oddly domestic. A drug induces torpor. Before departure, the crew deliberately put on body fat, the way a bear does before winter. Their pods are soft-shelled, darkened and cooled. They go under for the 180-day cruise. At the far end, 21 days of recuperation. And for the entire crossing, an artificial intelligence watches over 6 unconscious people who cannot watch over themselves. Jennifer Ngo-An, who leads the Sci-Spac team, put the prize plainly. If you could reduce an astronaut's basic metabolic rate by 75%, which is roughly what large hibernating animals like bears actually achieve, the mass and cost savings would be substantial enough to reshape what missions are possible at all. NASA runs its own version, called STASH, studying torpor in animals for space health in humans, and NASA frames the hazards of spaceflight with an acronym, RIDGE: space radiation, isolation and confinement, distance from Earth, gravity fields, hostile closed environments. STASH's long-term claim is that human synthetic torpor could mitigate or eliminate every hazard on that list. Every one, including the first. And that should stop you, because torpor is supposed to be about time, about skipping it. Why on earth would sleeping through a journey protect you from a cosmic ray? In 2022, a team published the answer in Scientific Reports. Angrini Puspitasari, Walter Tinganelli, Marco Durante and colleagues, working at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, alongside Gunma University's Heavy Ion Medical Center in Japan and the University of Bologna, ran an experiment on rats. Rats do not hibernate. That's the point of choosing them. Like us, they have no natural switch for this. The team induced synthetic torpor chemically, injecting a compound called 5'-AMP, and then held the animals in a room at 16 degrees Celsius, 61 Fahrenheit, roughly a cold cellar, for 6 hours. And they did this immediately after irradiating the animals with accelerated carbon ions. Not X-rays, carbon ions. Heavy nuclei, the same category of particle that does the deep track-cutting damage in deep space, produced by an accelerator built for exactly this kind of question. The rats in torpor survived a dose that killed the control animals. At lower doses, the histology told the story. In the brain, fewer activated microglia. Those are the immune cells that flare up when neural tissue is injured, so fewer of them means less injury to respond to. In the liver, fewer cells dying. In the lungs, less damage. The slowed, cooled body took less harm from the same radiation. And this is not a brand new discovery. Musakia and Barr showed back in 1968 that squirrels in natural torpor were protected from radiation. The findings sat in the literature for over half a century because nobody could induce the state in a non-hibernator, so nobody could use it. Which reframes the whole idea. Torpor may not be a trick for skipping time. It may be a radiation countermeasure that happens to skip time as a side effect. Some researchers now suggest first human trials could come within a decade, and the counter-argument is one sentence long. No human being has ever been demonstrated in extended metabolic suspension with full revival. Not once. Not for a week. The distance between a rat at 16 degrees for 6 hours and a person at low metabolism for decades is not an engineering gap you close with funding. It's a gap in what anyone knows. So go colder. Freeze them properly. That's the instinct, and it hits two walls. The first is water. Water expands when it freezes, and it freezes into crystals with edges. Those crystals form inside cells and tear the membranes apart. The cell isn't sleeping, it's shredded. It's the same reason a tomato that's been frozen collapses into mush when it thaws. The structure was destroyed while it looked perfectly intact. The second wall is stranger and worse. Chemistry doesn't slow down evenly. Different reactions have different sensitivities to temperature, so as a body cools, 10,000 biochemical processes all slow at different rates. A cooled body isn't a paused body. It's a body where every system has fallen out of step with every other one. Think of an orchestra where each instrument slows at its own pace. It doesn't get quieter and grander. It becomes noise. Vitrification is the way around the first wall. Replace the water with cryoprotectant chemicals and cool so fast that the water never crystallizes. It turns to glass. And it works. Routinely. Embryos, eggs, sperm, some tissues, every day, in clinics around the world. But scaling from an embryo to a person is not a scaling problem. It's a different problem. Every organ has its own tolerance, its own perfusion, its own poisoning threshold for the very chemicals keeping the ice away. And the brain sits at the worst possible intersection, the most sensitive organ in the body, and the one you cannot afford to lose any of. You cannot vitrify 95% of a person and call it a success. So the verdict is unglamorous, and it's the same one the physics gave us about engines, designed for people who live complete lives aboard, with everything that entails. Unless you take the shortcut all the way, send no adults, send embryos, or gametes, or just the sequences written down to be assembled at the far end. The ship gets radically smaller, cheaper and faster. No air, no crops, no rotation for gravity, no constitution, no factions. A seed, not a world. Automated systems would revive them at the destination, gestate them, raise them, and bootstrap a population from nothing. The engineering ask is severe. care and education systems that function flawlessly across centuries, with no adult present to notice when they don't. The ethical ask is worse, and it's not abstract. Those children would have no parents, no elders, no grandmother's story about a place called Earth, no oral tradition, nobody to explain at 3 a.m. why any of this is happening or what it means to be the thing they are. Every human being who has ever existed learned what a human being is by watching other human beings do it. These children would learn it from a machine's best reconstruction of a species none of them had ever met. The version that survives contact with reality is the hybrid, a crude ship carrying frozen embryos as a genetic reserve, a library of variation from founders long dead, available if the living population narrows, and it opens a question nobody has answered. Who activates the reserve? By what criteria? With what authority? Picture Generation 7 looking at a fertility curve bending downward, holding a decision written by strangers who died 300 years ago, which leaves the destination. And here, at last, is something to be genuinely proud of, because what we can do from 400 trillion kilometers away is extraordinary. Consider how you detect an atmosphere on a planet you cannot see. You watch it go around its star, and you measure the heat coming off it all the way around the orbit. That's a thermal phase curve, and the logic is beautiful. If a planet has an atmosphere, wind carries the day side's heat around to the night side, so the night side glows. If it has no atmosphere, nothing carries anything, and the night side is simply dead. You find the air by looking at where the heat isn't. The TRAPPIST-1 system sits 40 light-years away, 7 Earth-sized rocky planets around a red dwarf, the most common kind of star in the galaxy. If an Earth-sized world can hold on to air there, then such worlds are everywhere. So the Webb telescope looked. Using its mid-infrared instrument at 15 microns, astronomers measured the phase curves of the 2 innermost planets. TRAPPIST-1b's dayside registers 490 Kelvin, give or take 17. That's 217 Celsius, 423 Fahrenheit. A domestic oven turned to its highest baking setting, and the night side shows nothing, no detectable emission, no phase offset at all. A blazing day, a dead night, and nothing moving between them. That combination has one honest reading. There is no air. TRAPPIST-1c runs cooler, 369 Kelvin on the dayside, about 96 Celsius, just past boiling, with a night side statistically indistinguishable from B's. For both planets, models with surface pressures at or above 1 bar, the pressure you're sitting in right now, are strongly disfavored. Then TRAPPIST-1d, sitting on the edge of the temperate zone. A team led by Caroline Piolet-Goroyeb pointed Webb's near-infrared spectrograph at 2 transits and searched for the molecules that make Earth. No water, no methane, no carbon dioxide. Their honest conclusion allows 3 readings. An atmosphere too thin to see, like Mars, thick high clouds hiding everything beneath like Venus, or a barren rock, and TRAPPIST-1e, the one in the habitable zone, the best candidate in the best studied system we have. In September of 2025, 2 teams published the first Webb results from 4 transits. The primordial hydrogen, the light original atmosphere the planet formed with, is gone. Then they wrote the sentence. With the current data set, they are unable to distinguish between an atmosphere and no atmosphere at all. Nitrogen-rich air with traces of carbon dioxide and methane, permitted by the data. Bare rock, also permitted by the data. Surely 4 hollow inner planets condemn the rest. Joshua Chrysanthon-Toton published exactly that argument, and his answer is no. The outer planets take far less X-ray and ultraviolet punishment from the star. What killed the inner worlds tells you much less about the outer ones than instinct insists. The framework for all of this is called the cosmic shoreline, proposed by Kevin Zarnley and David Catling in 2017. Plot every world by how hard its star has blasted it against how strongly its gravity holds on, and a line appears across the graph. Above the line, stripped bare. Below it, air retained. In our own solar system, it works remarkably well, and it is contested visibly right now. Open the papers being published this year and you'll find 3 different shorelines drawn across the same axis. Zarnley and Catling's original, a refined version from Pass and colleagues, and a retention probability line from G and colleagues. Same physics, same planets, 3 different boundaries. Webb's Rocky Worlds program, running on directors' discretionary time, is testing that boundary now, world by world. In late 2025, it added another point, GJ3929b, likely a bare rock. And the honest obstacle isn't the planets at all, it's the stars. Red dwarf surfaces are mottled with dark spots and bright faculae, and that unevenness contaminates the spectrum. The distortion changed between all 4 visits to TRAPPIST-1e. Sometimes the star is simply louder than the planet. Now here is the part that undoes everything above. Every observation we make today is centuries stale by the time the ship arrives. Stars flare, and red dwarfs flare violently. Planets have weather, they have volcanism. Orbits evolve. Atmospheres come and go. A crew arriving at Proxima or TRAPPIST-1 would be acting on data older, relative to them, than the printing press is to us, and betting their children's lives on it, which forces the last requirement. The ship must carry its own instruments, its own expertise to read them, and its own authority to decide what to do, because Earth's opinion, if it arrives at all, will be decades out of date at the moment it lands. So how does this actually end? 3 ways. The version that works looks like this. The knowledge is intact, the reactors are running, the purpose still holds, and in the forward window there's a star that is very slowly brightening year by year, a sunrise 400 years long, watched by people who will hand it to their grandchildren. The version that fails suddenly is a reactor that cannot be contained, a breach that cannot be repaired, a disease moving through a population whose immune systems have narrowed in a place with nowhere to run. And the version that fails slowly is the one that should frighten you. Checklists followed without principles. Drift, a bottleneck that shows up first as a number in a fertility report. Factions that gradually stop speaking to each other and then stop maintaining each other's systems, because the sudden failures at least announce themselves. Alarms sound, people run, somebody fights. Slow failures trigger nothing, no alarm, no threshold. They are visible only in retrospect, as a trajectory bending, very gently, in the wrong direction, over 100 years that felt entirely normal to everyone living through them. And if that's true, then the ship cannot be saved by watching for it. It can only be saved by what was built into it before anyone ever closed the door. Think about what that actually demands of the people who build it. You must design a countermeasure against a failure you will never witness, that produces no signal, in a society that will not exist for 200 years, using materials that will be obsolete before anyone sails. You cannot iterate, you cannot test, you cannot fix it later, because later is a century after your funeral. You get one pass, and the thing you're defending against is not a crack in a hull, it's a slow forgetting. So how do you engineer against that? The first answer is architectural, and it's counterintuitive. Don't build a single community, build several. The city-state model, semi-autonomous communities, each running its own affairs, sharing the ship's infrastructure, power, air, water, the reactor, under one common framework that none of them individually controls. It sounds like unnecessary complication. It does 3 things nothing else does. Power cannot concentrate. No single administration owns the whole ship, so no single bad decade can capture it. On a 250-year voyage with nowhere to emigrate to, that matters more than any hull. It runs experiments. Different communities try different things, different schooling, different work structures, different ways of settling disputes, and the ship watches in real time from the inside and learns which ones drift. And it creates redundancy for the thing that has no other backup. If one community loses its skills, its cohesion, its grip on why the reactor is built the way it is, the others still have it. Somebody can walk over and teach it back. That's the difference between one enormous file and a distributed archive. Corrupt one copy and the information still exists. And it's the difference between a monoculture and a rainforest. A field of identical wheat is efficient right up until the day one disease arrives. Now the second answer, and this is the one people dismiss on first hearing. You design the culture, deliberately. Rituals, stories, symbols, institutions, built from the start to survive generations. Not allowed to emerge, engineered. And art, music, sport and celebration are not luxuries you permit if there's spare capacity in the budget. They're load-bearing structure. Here's why, and it isn't sentimental. A purely transactional society loses its resilience and its belief long before any physical system fails. Give people only functions to perform, and they will perform them competently for decades. And then, at 3 a.m, when something is going wrong that isn't in anyone's job description, they will go back to bed. The reactor does not get saved by a checklist. It gets saved because somebody's daughter is asleep on the other side of that bulkhead, and because they believe the thing they're all doing is worth staying up for. You cannot install that in year 200. You have to build the ship around it, and remarkably, when someone finally ran this as an open engineering problem, that's exactly how they scored it. On the 1st of November 2024, the Initiative for Interstellar Studies, a UK-based non-profit, launched the Project Hyperion Design Competition. Prize pool, $10,000, split 5, 3 and 2. The brief was specific. Habitability for 1,000 people, plus or minus 500, over centuries. A 250-year journey to a habitable planet. Current or near-future technology only. No warp drives, no wishful physics. And then the entry requirement that makes the whole thing extraordinary. Every team had to include at least one architectural designer, one engineer, and one social scientist. Not encouraged to, required. You could not submit without all three. Sit with what that means. A serious interstellar design competition run by people who take this seriously, formally declaring that a spacecraft designed by engineers alone is an incomplete answer. The rules said it. Before anyone drew a single line, teams entered from around the world. The detailed design phase closed on the 20th of May, and the winners were announced in London on the 23rd of July, 2025, judged by a panel of A. Scott Howe of NASA's Jet Propulsion Laboratory, Olga Bonova of the University of Houston, Madhu Thangavelu of the University of Southern California, and Elena Rocci of Arizona State University. 10 teams took honorable mentions. Chrysalis won. An Italian team, Giacomo Infelice, Veronica Magli, Guido Sprogio, Nevenka Martinello and Federica Chiara Serpe. Architects, astrophysicists and psychologists working together. The object they drew is 58 kilometers long, 36 miles, and 6 kilometers across, nearly 4 miles. Manhattan Island is about 13.5 miles end to end. Chrysalis is close to 3 Manhattans laid nose to tail, and it flies. Its mass is 2.4 billion metric tons. The International Space Station, the largest structure humanity has ever assembled in orbit, 25 years and 100-odd launches in the making, weighs about 420 tons. Chrysalis masses roughly 5.5 million of them. The layout is a Russian nesting doll. Concentric rotating shells around a central core, each with a job. The outermost shell is the armor, radiation and micrometeoroid shielding. And it does not just sit there. It doubles as the warehouse, tools, spare parts, raw materials, largely handled by robots. So the layer taking the damage is the layer with the fewest people in it. Move inward and you reach industry, recycling plants, workshops, pharmaceutical labs. Inward again, housing, with its own air circulation and temperature control. Power comes from a direct fusion drive burning helium-3 and deuterium. It accelerates for about a year, then coasts for 4 centuries toward Proxima Centauri b. The shape is a decision, not an aesthetic. A long, narrow cylinder presents the smallest possible frontal cross-section, the smallest target for everything it has to plow through, and less structural stress under acceleration. But the detail I keep returning to is the rotation. Spinning a shell creates gravity. It also creates forces that fight the shells next to it, a stack of counter-torques, each layer trying to twist its neighbors for 400 years. So the design offers an alternate configuration. Odd-numbered shells rotate clockwise, even-numbered shells rotate counterclockwise. The same principle keeps a twin-rotor helicopter from spinning itself in circles. Turn 2 things opposite ways, and the torque cancels. The ship stops fighting itself, and at the front they put the Cosmodome, a low-gravity space with a panoramic view of deep space. You go up there and you float, and you look out at the stars, and there is nothing between you and the galaxy. Now, the cynical read is obvious. That's the sci-fi shot. That's the poster. Except think about what a brain in there is actually receiving. Depth, distance, a horizon that isn't a wall curving back at you. Something to look at that is different tonight than it was last year, because the ship has moved and the sky has shifted. That dome is not decoration, it's a prescription. It's architecture written against the specific, measured damage that monotony does to the human hippocampus. A room designed to give a brain the one thing the rest of the ship structurally cannot. Designed psychology, poured in metal. The second place entry, WFP Extreme, came from a team in Krakow. 2 enormous counter-rotating rings linked to a central core, organized not into modules but into districts and neighborhoods, connected by what they called taxi capsules, and read what the jury praised it for. Consistency, yes, but specifically its cultural and societal ideas, naming as examples clothing and spiritual places, clothing and places to pray, a spacecraft competition judged by NASA JPL, awarding points for what people wear and where they go to be quiet, because across 2.5 centuries, those are structural members. Third place went to Systema Stellar Proximum, 2 counter-rotating Stanford Tauri, classic ring habitats, nested inside a hollowed-out asteroid. The rock does the shielding. The mass you never had to launch does the job the mass budget could never have afforded. And look at who built it. Philip Koshy, a professor of mechanical engineering at McMaster University. Jan Johan Ipe, a physician. Amaris Ishana Mathen, a graphic designer. An engineer, a doctor, and a graphic designer. The jury's praise was for their storytelling. But underneath every one of these designs sits a tension nobody solved, because it may not be solvable. Larger populations are more robust, more genetic reserve, more redundant expertise, more cultural resilience, more people to notice, and every additional person is mass. Mass is fuel, and fuel is mass, which needs more fuel. The 2 curves point in opposite directions and there is no clean crossing point, which is exactly why the estimates from under 100 to over 40,000 have never converged. They're not answering the same question. One architecture threads it. Don't build one ship. Build 10 to 20 mid-sized ships and fly them in formation. They can assist each other. Transfer crew when a community fractures. share genetics without any single hull carrying the whole reserve, run genuinely independent governance experiments in physically separate worlds, and compare. And the real prize, one loss becomes a tragedy instead of the end of everything. A hull breaches, and the species does not end with it. The price is brutal and honest. Launch cost rises sharply, redundant reactors, redundant hulls, redundant everything, for a mission that was already the most expensive object ever contemplated. You buy survival probability with money. Nobody has priced it, and nobody wants to be the one who says how much a species is worth. But all of it, every shell, every ring, every fleet, shares one unsolved problem, and it's the one that quietly turns a starship into a bullet. Deceleration costs as much as acceleration. Roughly speaking, the reverse burn doubles the mission's fuel, and it's worse than doubling because you have to carry the braking propellant the entire way and accelerate it to cruise speed too. You spend fuel to move the fuel that will one day stop you. Drive across a continent carrying every drop of the return trip in the trunk and pay for that weight at every mile. Launch without a deceleration plan, and you have not built a mission. You've built an extraordinarily elaborate flyby that takes 4 centuries and crosses its destination at 30,000 kilometers per second, nearly 19,000 miles per second, with everyone aboard watching the only world they were ever going to have shrink in the rear window over about 90 seconds, which is why the best idea in the field arrived by accident. In 1988, Dana Andrews was working on a magnetic scoop, a way to gather ions from space to feed a nuclear electric ion drive, a Bassard-style ramjet without the fusion. He asked Robert Zubrin to help him compute one thing: how much drag the scoop would create against the interplanetary medium. Zubrin ran the numbers, and the answer was fatal. The drag the scoop generated was far larger than any thrust the ion drive could ever produce. The engine wasn't inefficient. It was a brake with a motor attached. So Zubrin proposed the inversion. Throw away the drive, keep the scoop. Andrews agreed, and the magsail was born, out of a calculation that killed the thing it was meant to save. The device is beautifully simple, a loop of superconducting cable generating a magnetic field which deflects the ionized plasma the ship is ploughing through. No propellant, no fuel, no tanks. It drags on the galaxy itself. Zubrin's own assessment cuts to it. The interesting thing about the magsail is not what it does to speed a craft up. It's the slowing down. He called it the ideal interstellar mission brake, and in their paper, Andrews and Zubrin put a number on it. Used as a brake, the magsail reduces a spacecraft's velocity by a factor of e every 5 years, e being the mathematical constant, about 2.7. So every 5 years, the ship's speed drops to roughly 1/3 of what it was. A handful of 5-year steps and you've gone from 1/10 of light speed to something you can live with, if it works. In 2017, Claudius Gross at the Institute for Theoretical Physics at Goethe University, Frankfurt, went back to the problem and did it differently. Zubrin and Andrews had modelled the plasma as a fluid pushing against a bow shock. Gross instead integrated the equations of motion for individual interstellar protons hitting the superconducting loop and calculated the effective reflection area as a function of the ship's velocity, how much of the incoming plasma the field genuinely turns around. Then he ran their own parameters. Their loop, 100 kilometers in radius, about 62 miles. Their velocity, 750 kilometers per second. His answer is substantially more conservative, and his paper says the uncomfortable part out loud. Andrews and Zubrin's scaling relations, he writes, are inconsistent with his results, and the reason for the discrepancy is unclear. Nobody knows why they disagree, and it gets worse. At the mission parameters Zubrin and Andrews proposed, Gross's analysis places the craft right at the point where the interstellar protons are not reflected at all, where the effective reflection area vanishes to nothing. Not a weaker break. Barely a break. So which is right? Nobody knows, and nobody can settle it, because settling it requires deploying a superconducting loop 60 miles across in real interstellar plasma. The experiment is the mission. There is one thing both sides agree on, and it's a genuine weakness. The magsail's grip depends on speed. It's superb when you're fast, and it fades as you slow, which means it gets weakest exactly when you most need to stop. A parachute that works beautifully at terminal velocity and does nothing at walking pace, which is why Nikolaos Parakis and Andreas Hein, working within I4I's Project Dragonfly, proposed combining magnetic and electric sails, one brake for the fast phase, a second for the slow tail, and gravitational braking, swinging past the star and the planets to shed velocity. Elegant, free, and useless as a plan, because it works only inside a system whose exact configuration you cannot see until you're already inside it, arriving at a tenth of light speed with no second attempt. And all of that assumes you arrive at the right place. No GPS, no ground stations, no mission control quietly nudging the trajectory. Stellar navigation is the oldest technology our species has. Polynesian navigators crossed the Pacific by it. Phoenicians ran the Mediterranean by it. Every sailor before satellites steered by the fixed lights overhead. Except they aren't fixed. Not for you. Travel far enough and parallax reshapes the sky. The nearby stars slide against the distant ones. The same way, driving down a road, the near trees rush past, while the far mountains barely move. Except now, the road is light years long. The constellations you launched under deform, then dissolve, then become something with no name. Your entire reference frame is being rewritten by your own motion, continuously, for centuries. And here's the part with teeth. A tiny error at the beginning, sustained across decades, does not produce a slightly wrong arrival. Aim a rifle a hair off, and at 10 meters you're fine. At 4 light years, you are not in the same neighborhood as the target. You cross empty space at a tenth of light speed, and there is nothing to stop against, which means Generation 150 must hold Generation 1's instrument precision, and, harder, Generation 1's cultural rigor about why precision is worth the trouble, and no one is watching over their shoulder. When Voyager 1 crossed the heliopause, its signals took roughly 17 hours to reach Earth. Send a question at breakfast, hear back the following morning. That was inside our own solar system. 1 light year means 1 year each way. At Proxima, that's 4¼ years out, 4¼ years back. 8½ years for one question and its answer. Halfway there, every message from Earth is a reply to a situation that resolved itself years ago. Every instruction is advice about a crisis that is already over, survived or not. No help arrives in time, not because nobody cares, because the universe does not permit it. So what can Earth still send? Not help, continuity, news, science, art, music, the sound of human voices from the world they came from, proof that the place still exists, still thinks, still makes things. And that link doesn't end on a date. Nobody switches it off. It fades. The voices get quieter. The news arrives later. The threads thin. And somewhere out there a generation grows up, for whom Earth's transmissions are a background hum nobody bothers tuning into, until one day someone checks the log and realizes nobody has listened in 11 years. Full autonomy is not a design choice anyone gets to make. The physics of light imposes it, on schedule, ready or not. So that's the ship. Counter-rotating shells, a dome full of stars, a city of city-states, a superconducting loop dragging on the galaxy, a constitution with bedrock and topsoil, $10,000 in prize money, and a jury that gave points for clothing and for places to pray. Every single piece of it exists for someone, and that someone has not been born yet. We'll not be born for 100 years. We'll never see Earth, never meet the designers, never read the competition brief, and never once be asked. We have spent all this time designing the vessel. We have not yet asked what the vessel makes of the people who wake up inside it. Here's the reframe that changes everything about how you look at this. Children are not a consequence of the generation ship. They are not a complication the designers have to manage or a happy detail in the brochure. They are the mechanism. The fusion drive carries the mass. The children carry the mission. Take them out of the design and you no longer have a starship. You have an extraordinarily expensive coffin with excellent life support, coasting toward a star nobody will be alive to see. Every other system aboard exists to keep the reactor running. The children are the only system that keeps the purpose running, and they chose none of it. A sky that does not move, wind that arrives because a fan switched on, seasons because a lighting schedule says so, rain, if there is rain, on a timetable, from a maintenance calendar written before their grandparents were born. So what does that do to a person? Your instinct is that it's a deprivation, that a child raised under metal has been robbed of something and will feel the shape of the missing thing. Developmental research says otherwise, and the answer is more unsettling than the fear was. Children calibrate. A developing brain does not measure its world against a better one it has never seen. It builds itself around whatever it is actually given, and that becomes the baseline for everything. You did this. Whatever you grew up inside, a particular city, a particular language, a particular set of assumptions about what a normal Tuesday contains, you did not experience it as the absence of every alternative. You experienced it as reality. The comparisons came later, if they came at all. To a child born aboard, the ship is not instead of Earth. The ship is simply the world. No felt deprivation, no sense of loss, no basis for comparison, because comparison requires a second thing. They will cope, fully, happily, probably, and they will be different, and you cannot have the first without the second. Watch Earth recede, not through the window, but through the generations. Generation 1 remembers. Actual sensory memory. The smell of cut grass after rain, the exact grey of a particular winter sky, a brother who stayed behind, and whose face is now fixed at the age he was on the launch pad. Generation 2 gets the stories. First-hand, vivid, told by someone who was there. But stories. Generation 3 gets stories about stories. The details start rounding off. The grass smells like whatever their mother said grass smells like. By generation 5 or 6, Earth is not a place. It's an origin. Think about Rome. You know it existed. You've seen photographs. You could probably name 3 Romans without looking anything up, and it has precisely zero purchase on how you spend your afternoon. That is what Earth becomes to the shipborne. Real, documented, historically important, and completely irrelevant to living. And the destination undergoes exactly the same erosion, running the other way. A promise made by the deep past about a place nobody aboard has ever seen. Now, the biology. And the first system is invisible. In 1989, a British epidemiologist named David Strachan was working through data from a cohort of British children, tens of thousands of them tracked from birth. He was looking for what caused hay fever. He found something backwards. The more older siblings a child had, the less hay fever they got. More children in a house means more shared germs, and more shared germs somehow meant fewer allergies. Strachan proposed that infections in early childhood protect against allergic disease, and the hygiene hypothesis was born out of a correlation nobody was looking for. Now, be careful here, because this is a field that has argued with itself for 30 years. The original version has been revised, extended, and criticized. There are researchers who think the name should be abandoned entirely because it was never really about cleanliness. The strongest current framing comes from Graham Rooke, and it's called the old friends idea. The microbes that matter aren't colds and measles. They're the ancient ones, from soil, from animals, from other people's skin, the organisms that were present while the human immune system was evolving, and which that immune system therefore expects to meet. Then came the alpine farm studies. Children raised on Central European farms, drinking unprocessed milk, in daily contact with animals, encountered a dramatically wider range of microbes and had markedly less asthma and allergy than children who didn't. And in 2019, in Nature Medicine, a team published the finding that should stop every habitat designer cold. Farm-like indoor microbiota in non-farm homes protects children from developing asthma. Read that again. Not the farm, the microbes. You can have the protective effect without the barn if you deliberately engineer the microbial environment of the room, which promotes the ship's microbiome from a housekeeping detail to a life support parameter. Specified, monitored, adjusted, as carefully managed as oxygen partial pressure, because it does the same job on a slower clock. And the engineering instinct here is exactly, catastrophically wrong. Sterile feels safe. Sterile is a slow immunological disaster on a 200-year fuse, a population whose immune systems were never taught what to ignore, meeting an unfamiliar world at the far end. The ship must be deliberately diverse, deliberately dirty, deliberately managed, which is the strangest engineering requirement in this entire subject. The next system is one you're standing on. Bone is not inert scaffolding. It's living tissue that constantly tears itself down and rebuilds, and the rebuilding is driven by load. Push on it, and it thickens where the pushing happens. Stop pushing, and it dissolves what it isn't using and reclaims the calcium. It's the same logic as a callus. Use the hand, get the skin. Stop, lose the skin. So a child growing up at 8/10 of Earth gravity does not get slightly weaker bones. They get a skeleton built to a different specification, laid down during growth to match the loads that were actually there, and deviations compound. Generation 1 adapts, because Generation 1 arrived with Earth-built skeletons and is merely losing ground from a known baseline. Generation 5 is being built from Generation 4's baseline, which was built from Generation 3's. By then, it isn't adaptation, it's a population. And then there's the one nobody expects, and I find it the most quietly astonishing constraint in the whole design. Childhood myopia, short-sightedness, is climbing sharply across the world, and it's now a serious public health concern. The most consistent finding in the research is startlingly simple. Time outdoors protects against it. Why is still argued. The leading candidate is bright light, and how much of it reaches a growing retina. Viewing distance is another. The mechanism isn't settled, and honest researchers say so. But here's the thing. For the ship, both candidates produce the identical requirement. A child raised in corridors, under artificial light, with nothing further away than the far bulkhead, is a child whose eyes are developing without an input they evolved to expect, which means habitat architecture must engineer sight lines long enough for eyes to grow correctly. Sit with that. Not a design preference, not an aesthetic, a medical requirement expressed in meters. The distance you can see is a health parameter. On a ship where every single meter costs fuel, twice, all of which lands on the number that sets the entire vessel. Artificial gravity comes from rotation. Spin a cylinder, and everything inside gets flung outward until the floor stops it. The floor pushes back on your feet, and your body has no way to tell that from weight. Physically, it is weight. But rotation charges a fee, and the fee is in your skull. Turn your head inside a rotating room, and your inner ear receives a signal that doesn't match what your eyes report. Your head's rotation cross-coupling with the room's. The result is nausea, disorientation, and things going wrong when you reach for them. It's the feeling of trying to read in the back seat of a car on a winding road, except the car is the room, and the road never ends. So the question that sizes the entire ship is this: how fast can you spin a world before the people inside are permanently ill? The classic answer came from Stone and Letko in 1965, resting on Ashton Gray Beale's slow-rotating room experiments. Their comfort zone tops out at 6 revolutions per minute at a radius of 12 to 24 meters, 40 to 80 feet. And now the honest part, which the field states about itself. Very little experimental data was ever collected to validate that model. Those limits came from watching people walk, climb, and move objects around in a centrifuge and drawing the boundary where it looked uncomfortable. Al Globus and Theodore Hall took 5 historic studies and composited them into a single comfort chart and landed somewhere far more conservative. 2 RPM, they argue, is the threshold acceptable to most people. Many researchers now use that as the working number. Then Lawrence Young and colleagues in 2001 showed subjects adapting quickly to head rotation during centrifugation at 23 revolutions per minute. 23. Gray-Beale found 10 RPM tolerable if the exposure was gradual, and in his own 15-foot rotating room, at 1 RPM, even the most susceptible subjects were essentially symptom-free. 2, 6, 10, 23. That is not a rounding error. Watch what it does to the ship. Radius scales with the inverse square of the rotation rate. Halve the spin and you quadruple the radius you need. Run the arithmetic for 1 Earth gravity. At 6 RPM, a radius of about 25 meters, 80 feet, a large building. At 2 RPM, about 224 meters, 735 feet, a structure most of a kilometer across. At 1 RPM, roughly 900 meters, nearly 3,000 feet, a world almost 2 kilometers, well over a mile from wall to wall. Same gravity, same physics, same laws, and the entire diameter of the world, every kilogram of hull, every gram of shielding, the whole fuel budget, hangs on a physiological question nobody has answered. Because answering it properly means spinning human beings for years, and nobody has ever done it. Notice what's hiding underneath too. The 23 RPM result is about adaptation, trained adults habituating for an experiment with a non-rotating world waiting outside the door. The ship isn't asking adults to adapt, it's asking children to develop inside it. Nobody knows what a growing inner ear does when it has never once had a still reference. The most famous answer to this began as a homework assignment. In the early 1970s, Gerard O'Neill was teaching undergraduate physics at Princeton, and he set his students a problem: design large structures in space. Not to escape anything, to show that living out there could actually be desirable. What came out of that seminar he published in Physics Today in 1974, and expanded in his 1976 book The High Frontier? Island 3. 2 counter-rotating cylinders, each about 6.4 kilometers across, 4 miles, and 32 kilometers long. 20 miles. That's a radius of 3.2 kilometers, 2 miles. At 1 Earth gravity that spins at roughly half a revolution per minute. 1 full rotation every 2 minutes. Watch it from outside, and you would barely be sure it was turning. The counter-rotation isn't decoration either. A single spinning cylinder is a gyroscope, and a gyroscope resists being aimed. It would fight you every time you tried to point it at a star. Spin 2 of them opposite ways, link them, and the gyroscopic effect cancels out. The same reason a heavy-lift helicopter runs 2 rotors turning against each other. And at that radius, Coriolis effects drop below the threshold at which a walking human can perceive them at all. You throw a ball. It goes where you threw it. Inside, O'Neill ran 6 stripes the length of the cylinder, 3 transparent windows, 3 habitable land surfaces. Habitable area, about 325 square kilometers, 125 square miles. And on that land, real terrain, actual soil, not hydroponic trays, trees with roots, rivers, and a volume of air large enough that it circulates on its own, forms clouds, and produces weather that nobody scheduled. Imagine standing there. The ground under your feet feels exactly like ground. No lightness, no floating, nothing to notice. But look toward the horizon, and it doesn't fall away. It rises. The landscape sweeps up on both sides, and if you follow it with your eyes, there are rivers and forests hanging 4 miles above your head, upside down, in full daylight, with tiny weather of their own. And the sky is open, genuinely open, not a ceiling 4 feet overhead, but a real depth of air, with distance in it, where clouds form and it rains on you because the physics decided to. That solves the eyes, it solves the bones, it may even solve the shrinking hippocampus. Whether it defeats the knowledge that the sky is a machine, nobody has data on that, and nobody can get any. You can engineer the distance, you cannot engineer the not knowing. So what happens to a human body when the gravity simply isn't there? We ran the experiment exactly once, and we can never run it again. Scott Kelly spent 340 days aboard the International Space Station from March of 2015 to March of 2016. His identical twin brother Mark stayed on the ground, a genetically matched control, which is a thing science almost never gets. More than 300 samples across 27 months, analysed by labs across the country, published in Science in 2019. The good news is substantial, and it deserves to go first. Roughly 91.3% of the observed changes reverted to baseline after he came home. His immune system stayed fully functional. He received a flu vaccine in orbit and responded exactly as he would have on Earth. NASA's own assessment is that the gene expression shifts likely sit within the range you'd find in any human under stress. A mountaineer, a scuba diver. Michael Snyder at Stanford summed it up. Thousands of molecular changes go up with you, and virtually all of them come back to normal within 6 months. But about 7% did not. And look at the list of what stayed changed. Genes governing immune function, DNA repair, bone formation networks, the body's response to low oxygen and to excess carbon dioxide. Every single one of those is a system the ship is betting on. Then the telomeres. Telomeres are protective caps on the ends of your chromosomes. They shorten a little every time a cell divides, and they're one of the most reliable molecular proxies we have for biological aging. Every prediction going in said Scott Kelly's would come back shorter. Radiation, disrupted sleep, confinement. A year in the harshest environment a human being has ever endured. They got longer. Susan Bailey's team at Colorado State assumed a sample handling error and reran the assays. The lengthening was real and substantial and sustained throughout the mission. Then he landed, and within roughly 2 days, the majority of them shortened, leaving him, in the end, with more critically short telomeres than he'd had before he left, alongside chromosomal inversions that persisted for years. The body did something remarkable up there, and then it paid for it on the ground in 48 hours. NASA's position is measured and defensible, stretching from a standard 6-month rotation to a full year, produced no significant decrease in Scott's cognitive performance while in flight, measured against his twin. The drop in speed and accuracy came afterward, and NASA notes it may well reflect readjusting to gravity, plus the brutal schedule that swallowed him the moment he was back. Matthias Basner at the University of Pennsylvania, a co-author, watched it over the following months and put it less comfortably. It wasn't getting worse, it also wasn't getting better, and the sharpest caution comes from outside the study entirely. Carol Greider, a Nobel laureate in molecular biology, not involved in the work, pointed out that we don't actually know how telomere length varies between ordinary twins on Earth. Without that, there's no baseline expectation to measure any of it against. 1 astronaut, low Earth orbit, behind the magnetosphere. 1 year, not deep space, not centuries, and not children, not longer, different. Which is the sentence that matters most. The temptation is to treat this as arithmetic. If a year does that, 400 years does 400 times as much. It does not work that way, and understanding why is the whole point. Scott Kelly went up as a finished adult and came home to a planet that could repair him. Every countermeasure in that study, every recovery curve, assumes a baseline to return to. The shipborne have no baseline. Their bodies are not adapting to the ship. Their bodies are being built by it. The skeleton, the eyes, the inner ear, the immune system, the brain. During the exact developmental windows when those systems are still being written and cannot be rewritten later. That is not a longer version of the same challenge. It is a categorically different one, and we have no data on it whatsoever. After 10 generations, the people aboard are genuinely unprecedented in human history. Not a colony, not an island isolate, something that has never existed. And underneath every measurement sits the thing you cannot calculate. Launching means deliberately creating people who had no say in any part of their world. Not the sky, not the gravity, not the government, not possibly their own genetics, not the destination they will spend an entire life approaching and never reach. Yes, every parent creates someone who never consented to existing. That's the human condition, and it isn't an argument. But every parent on Earth hands their child a world with doors in it. Other countries, other lives, other choices, and outside. The founders hand their descendants a world with no doors, knowingly, deliberately, on the strength of a promise about a star. Nobody has resolved that. Nobody has proposed a framework that survives 10 minutes of contact with the question. And here is the strange, genuinely hopeful thing, the reason none of this is wasted even if no ship ever launches. Every question here is a forcing function. Ask how to keep 1,000 people healthy for 4 centuries, and you are forced to answer, precisely and in numbers, how gravity builds a skeleton, how light builds an eye, how microbes build an immune system, how the shape of a room builds a mind. Those answers do not have to wait for a starship. They're needed for a lunar base now. They're needed on Mars now. They're needed in a hospital ward, a school, a city. The generation ship is the most extreme question we know how to ask about how to keep human beings human. And the answers arrive early, and they arrive here. But we are not finished with the ship, because we've talked about the reactor, and the air, and the crew, and the sky, and now the children. And everything still breaks, including the machines that make the replacements. Think about how many things in your home have quietly failed and been replaced in the last 10 years. A washer, a bulb, a hinge, a hose that split. Nothing dramatic, just the ordinary, relentless surrender of objects to time. Now put that in a sealed cylinder for 400 years. Pumps, seals, bearings, membranes, circuit boards, lights, valves, filters. Every single one has a service life, and every single one will reach it, and then reach it again and again, roughly 40 times over the course of the voyage. So the ship carries spares, and Decade 1 runs on those spares beautifully. Decades 2 through 5 run on fabrication. The ship stops unpacking and starts making. Lathes, presses, printers, furnaces, chemistry, and then the fabricators fail. That's the layer almost nobody models. You don't just need to make the pump, you need to make the machine that makes the pump, and then the machine that makes that machine, using tools that are themselves wearing out. A pantry runs out. A farm, in principle, runs forever, but only if you can also make the plough, and the forge that makes the plough, and the ore that feeds the forge, which means the ship needs full-depth industry, metalworking, polymers, electronics, glass, ceramics, biologics, textiles, not a workshop with good tools, a small industrial civilization, complete, with no external supply chain and no imports, ever. And this is where the knowledge problem finally shows its teeth, because you cannot run that on procedures. Somewhere in year 112, someone will open a document, follow the steps exactly, and the machine in front of them will not match the words on the page, because it was modified in year 60 and the note was lost. Only someone who understands the principle can proceed. Everyone else stops, so the verdict is short and cold. A ship without full manufacturing capability isn't a starship at all. It's a clock. The second invisible layer is law, and it starts from a fact so obvious that almost nobody states it. Whatever nation builds that ship, its writ ends at the airlock. Not for political reasons, for physical ones. There is no court that can reach them, no warrant that can be served, no force that can be projected across 4 light years and 80 years of light delay. The crew are citizens of the mission and nothing else from the moment the door closes. So a complete legal system has to exist on day one. Rights, property, contract, harm, justice. Not sketched, finished. And property is where it turns. On Earth, property rights are state-backed. When you own something, what you actually own is a promise, guaranteed in the last instance by force that isn't yours. Aboard the ship, enforcement is entirely internal. The community is simultaneously the owner, the police, and the court. Air is shared by necessity. You cannot privatize the atmosphere inside a sealed cylinder. So is water. So is food. And yet autonomy requires that a person own something. Someone who owns nothing at all isn't a citizen. They're a component. Push too far communal, and it reads as oppression. Push too far individualist, and you breed resentment in a place with nowhere to storm off to. Punishment is worse still. Incarceration wastes a scarce person. You have 1,000 people, and every one of them is a skill you cannot replace. Locking one in a room for a decade is removing an organ to punish it. And exile means vacuum, which fits essentially no crime a human being can commit. So, restorative justice, community rehabilitation, whatever the answer turns out to be, it has to be designed in advance, not improvised in year 80 in the worst week of everyone's life by frightened people. Does history help at all? Partially, and none of it is clean. The Pacific offers the best case. A single ancestral population spread across thousands of miles of open ocean and diverged into distinct cultures, distinct languages, distinct technologies. Proof that a small founding group can seed something that endures for millennia and becomes genuinely its own. Colonial America offers the harder case. Small communities cut off for months at a stretch, surviving on adaptation, cohesion, and luck. And many of them didn't. Roanoke simply vanished. An entire colony, gone, leaving a word carved into a post. Settlements up and down the Atlantic collapsed before they'd accumulated enough knowledge to survive their second winter. But be honest about the comparison, because it flatters the ship. Those Pacific navigators arrived at islands with fish in the water and timber on the hills. Those colonists stepped off onto a continent. Every one of those communities was surrounded by a world that, however hostile, contained more. The ship contains what's in the hold. Still, the survivors share one lesson, and it's specific enough to be useful. Adapt your culture to your circumstances while preserving your core competencies. Rigidity kills, and so does its opposite. A society that keeps every ritual and forgets its metallurgy dies exactly as surely as one that refuses to change anything at all. Which brings us to the moment nobody models, because you can't. Boarding is not leaving a country. It's leaving a world. Not sunlight, the sun. That specific warmth on the back of your neck on an afternoon in a place you know. Rain that nobody scheduled, arriving because the sky decided. Grass, the smell of it after that rain. The ocean, not a picture of an ocean, but the fact that one exists, that it continues past the horizon, that it has its own weather and its own moods, and doesn't care about you at all. The closest analogy anyone reaches for is irreversible immigration, the migrant who boards knowing they will never go home. And it falls short in exactly one way, and that one way is the whole thing. The immigrant keeps the sun, they keep the sky, they keep the rain, the grass, the fact that a horizon is a real edge that moves away when you walk toward it. Everything changes except the world. The border keeps none of it, and yet people would go. That isn't optimism, that's the historical record. Every era produces people who trade safety for the frontier, and they have never once been in short supply. They boarded the Mayflower knowing what winter meant. They pushed outrigger canoes past the last sight of land with no method of returning, and their children inherit not just the ship, they inherit the choice. That may be the single most valuable thing the founders can hand down, more than the reactor, more than the archive, the demonstrated fact that a human being can choose something enormous and mean it. So, which star? On the 24th of August 2016, a team of 31 scientists, led by Guillaume Anglada Escudé of Queen Mary University of London, published in Nature. The story behind it is lovely. A hint had appeared in the Doppler data back in 2013, a well-isolated peak at 11.2 days. Not convincing, not dismissible either. So they built an entire public campaign around killing it or confirming it. The pale red dot, 2 years in the planning, using HARPS at La Silla and UVS on the Very Large Telescope, watching Proxima Centauri night after night through the first quarter of 2016. They confirmed it. Proxima B minimum mass about 1.3 times Earth's, an orbit of 11.2 days at roughly 7 million kilometers, 4.5 million miles, from its star. That's about a 20th of the Earth-Sun distance. Mercury sits 8 times further out than that, and Mercury is a furnace. Except Proxima's luminosity is only about 0.15% of the Sun's. So at that scorching-looking distance, Proxima B's equilibrium temperature comes out around 234 Kelvin, minus 39 Celsius, minus 38 Fahrenheit. Cold, but close enough to the melting point of water that with 1 bar of atmosphere over it, liquid water works. The nearest star to our Sun has a rocky planet in the right place, and red dwarfs make up roughly 3/4 of every star in the galaxy. If red dwarf planets can be habitable, then the universe is not scarce. It's crowded, which makes what happened 5 months earlier almost unbearable. On the 18th of March, 2016, while the pale red dot campaign was still running, months before anyone announced the planet, Proxima Centauri detonated. The Everoscope caught it, and the Everoscope is a wonderful machine, an array of small telescopes that photographs the entire accessible southern sky every 2 minutes. It wasn't aimed at Proxima. It's aimed at everything. The star brightened by a factor of about 68, and for less than a minute the nearest star to the Sun, a star far too faint to see with your eyes, became visible to the naked eye from a dark site. Somebody in the southern hemisphere could have looked up at exactly the right patch of sky and watched it happen. Nobody did. A robot did. The energy released was about 10 times greater than any flare ever recorded from Proxima, most of it in the first 10 minutes. Ward Howard, then a graduate student at the University of North Carolina at Chapel Hill, working with Nicholas Law, put that super flare together with 23 other large flares the Everoscope had logged over 2 years and calculated the rate. At least 5 super flares a year. Then they modelled what that does to an atmosphere. Charged particles from the flares generate nitrogen oxides in the upper air, and nitrogen oxides destroy ozone catalytically, the same class of chemistry that opened the hole over Antarctica, except delivered from outside 5 times a year, forever. Their result, published in the astrophysical journal Letters, 90% of an Earth-like ozone layer destroyed within 5 years, complete depletion within a few 100,000, and with the ozone gone, the ultraviolet arrives. That single superflare delivered enough UVC to Proxima B's surface to exceed, by roughly 100 times, the dose needed to kill Deinococcus radiodurans, a bacterium so radiation-hardened it survives what would sterilize almost anything on Earth. So that settles it. Proxima is dead. Except no. And here you have to be careful, because this argument is live. At a workshop the SETI Institute convened specifically to debate whether life could emerge on a red dwarf planet, Gibor Basri of the University of California, Berkeley, summarized the outcome bluntly. Nobody found a showstopper, and the objections do have a habit of falling. The oldest one held that a tidally locked planet's atmosphere would freeze out on the permanent night side and collapse entirely. That died in 1996, when Harberly and colleagues showed that roughly 1/10 of a bar of carbon dioxide is enough to carry heat around and keep the whole thing stable. 3-dimensional climate models have confirmed it repeatedly since. The magnetic field objection, that a tidally locked world spins too slowly to generate one, met Driscoll and Barnes in 2015, who showed that tidal heating of the iron core might sustain a magnetic field, or even strengthen it, and red dwarfs calm down. 2 or 3 billion years of violence and then quiet, followed by a stability lasting longer than the sun will grant Earth. A planet with a strong enough field, or a thick enough atmosphere, might simply survive what the models say it shouldn't, and then inherit an almost unlimited future. Nobody knows. Both sides hold real physics. Neither has the observation that ends it. And underneath the whole argument sits the geometry, which is stranger than the debate. Habitable zone planets around red dwarfs are likely tidally locked, one face permanently lit, one face permanently dark, and between them a ring of endless twilight. Imagine standing on that line. The star sits on the horizon and it does not move, it doesn't rise, it doesn't set, it hangs, swollen and red, low, unblinking, for your entire life. Behind you, unbroken night and a continent of ice. Ahead of you, unending day. Your shadow points the same direction from your birth to your death. There is no morning. There is no evening. The wind never stops, because it isn't weather. It's a permanent river of air running from the cold side to the hot one, and it will still be running 1 billion years after you're gone. That is what habitable may mean out there. So take the alternative. Tau Ceti, genuinely sun-like, 11.9 light-years away, and bright enough that you could walk outside tonight, under a dark sky, and find it. In 2017, Fabo Feng and colleagues at the University of Hertfordshire detected 4 planets there by measuring the star's wobble. The outer 2, Tau Ceti A and F, sit in or near the habitable zone. Their minimum masses are about 3.9 times Earth's, and that number is the problem. Analysis of the wider exoplanet population suggests worlds begin shifting from rocky to volatile rich somewhere around 2 Earth masses. At nearly 4, and that's a minimum, remember, the true masses are probably higher. There's a substantial chance both are mini Neptunes with no surface to stand on at all, wrapped for good measure in a massive debris disk that bombards them. So here is where we actually are. Our nearest options are red dwarfs, with everything that implies. Sun-like targets cost centuries more travel, and the nearest one's best candidates may not be places you can walk, which makes reconnaissance before launch worth as much as every engineering decision combined. Get the destination wrong, and the reactor, the Constitution, the children, the 400 years, all of it void. So look at what we've actually gathered. Reactors maintained by people not yet born. Ecosystems running with no universities behind them. Genetic bottlenecks that announce themselves first as a number in a fertility report. Governance that has to be legitimate for people who were never asked to sign. Knowledge decaying continuously, silently, with no alarm attached. Notice what almost none of that is. None of it is propulsion. The generation ship is not the spacecraft. It is the civilization inside it. And the civilization is, by an enormous margin, the harder engineering problem. So, how long could a generation ship survive in deep space? The honest answer is maybe, under very specific and extraordinary conditions. Extraordinary design care, every invisible layer modelled and built before launch, because there is no second attempt and no revision. Extraordinary governance, legitimate across 3 centuries and 12 generations of people who never consented, and extraordinary luck, which cannot be engineered at all. And one thing more, a founding culture that bequeaths not just the ship, and not just the knowledge, but the will to use both. Possible, not guaranteed, not likely without every single one of those, but possible is a significant word. Everything that makes the stars reachable at all lives, right at the edge of possible, that's where it has always lived. And here is the thing I keep returning to, and it's the thing I want to leave with you. We are already aboard one. Look at what this planet actually is, described in the language we've been using all along. A sealed world drifting through the dark. Shrink it to the size of an apple, and the layer of air you can breathe would be thinner than the skin. Its ecosystems recycle the atmosphere, the same closed loop that quietly broke inside a glass building in Arizona in 16 months because nobody thought to model the walls. A single star supplies all the power, and it cannot be refueled, repaired, or replaced. Generations inherit a world they did not make, did not consent to, and cannot leave. They live under rules written by the long dead, using knowledge that decays unless it is deliberately, effortfully passed on. No resupply ship, no rescue mission, no outside. Everything we launched with is everything we will ever have. Every kilogram of iron, every drop of water, every species, every idea worth keeping, loaded once 4.5 billion years ago, and never again. Which means the lessons of the generation ship are, in the deepest possible sense, the lessons of living here. Closure, recycling, governance for people not yet born, knowledge that has to be maintained or lost, a culture worth handing forward, and the recognition that everything breaks and somebody has to notice and care enough to look. We were never really studying a hypothetical spacecraft. We were studying ourselves at the one scale where the answers become impossible to misread. The ship offers no trick of physics that dissolves the hard part, no engine that makes the crossing easy, no drug that skips it, no shortcut that spares anyone the centuries. What it offers is precisely what we already have, a direction, a small community, and whatever they can build, whatever they can be, and whatever they can pass forward. The stars are 25 trillion miles away, and that is not the hardest distance. The hardest distance is between what we want to be and what we actually are. That is the distance a generation ship must close, and it is the only one that decides whether anyone arrives. But sit with that word for a second. Arrives. Nobody who boards ever does. Not the founders, not their children, not their grandchildren. Every one of them lives an entire life inside a machine they are maintaining for people they will never meet, repairing a pump for a stranger on the strength of a promise they have no way to check. And you already know how that feels. Someone fixed the pipe under your street before you were born. Someone planted the tree you once sat under on a warm afternoon and never thought about again. Someone taught someone who taught you. None of them saw where it went. They did it anyway. That's the whole thing. Not the fusion drive, not the star. Just the willingness to carry something you won't see finish. In 1918, Robert Goddard wrote this exact idea down, sealed it in an envelope, and locked it in a friend's safe. On the outside, he wrote that it should be read only by an optimist. Tonight, you opened it. Thank you for staying with me this long. If it meant something, a like and a subscribe is how I know. There are stranger journeys coming, and quieter ones. I hope you'll be there. Sleep well. You were never going to see the arrival. Neither was anyone who ever loved you. That was never the job. Good night.